All right, so what we'll do now is we'll quickly review the IRIS logistic regression solution, the thing that I've uploaded. So we talked about this exercise. We took some time to solve this exercise, and this is the data set that we have here. Sepal length, sepal width, petal length, petal width, and we are trying to predict the variety. As I told you, this is the kind of a multi-class classification that we are trying to do. So what is the difference between binary and multi-class? Binary is where we are trying to predict between two classes. So we have either yes or no. Okay, either you're diabetic or you're not diabetic. Either the cancer is malignant or the cancer is benign. So you have only one out of two answers that are possible. That is what we refer to as binary classification. Multi-class classification is where we have multiple possible answers that could come. So that is the exercise that we had here. And we are going about it. We are doing some basic data analysis. You can see the info method. We do not have any missing values. There are 150 rows of data. There are 5 columns. We already talked about the IRIS dataset. It's a very old dataset. It dates back to 1930s uh, and a very, very popular academic dataset that we have here. Next up, we are looking at the pair plot, something that we talked about in uh, the previous discussions. And you can clearly see from the pair plot that we have a very strong separation between the classes. So when I do the pair plot, we are able to see that sepal length, sepal width, petal width, the 4 features that we have, the classes, the different varieties of flowers that we have, like Iris setosa, Iris versicolor, Iris virginica, we are able to see a very strong separation between the classes. So you can see, especially with respect to the petal length and the petal width columns, specifically with respect to the petal length and petal width columns, we can see that the classes are very well separated. The varieties of flowers are very well separated. That means if, in other words, if we know the petal length, we can very accurately predict the variety of flower. So if we have a higher petal length, we know that it's a virginica. And if we have a lower petal length, we know it's a setosa. If we have a higher petal width, we know it's a virginica. And if we have a lower petal width, it will be a setosa. So by looking at the petal length and petal width, we can very easily separate the classes of flowers. The same thing we can do for sepal length also. Okay, so but if you see the sepal width is not a great feature, that means the classes are overlapping. That means if I just know the value of the sepal width, that is not enough for me to be very certain as to what type of flower it is. We are not able to see a very strong separation between the classes. So the pair plot is a wonderful way that tells us in a data set, are the classes well separated? If the classes are well separated, then generally my algorithms will do very well to separate the classes. We will have a higher accuracy in the classification model. But like we saw in the diabetes exercise in the previous discussion, that the classes were not that well separated, and which is why in the diabetes data set, we only got around 70% or 80% accuracy. Whereas in the cancer one, we touched close to 94, 95. And same in iris also, we will touch close to 94, 95% accuracy. A slightly more numerical way to identify the best features is using something called feature importance. So this is based on some other mathematical techniques like entropy and information gain, which I do not want to get into. But the concept part we talked about in the previous discussion, where you can use feature importance and you can see that uh, the relative importance values of the features. So one is the visual approach, and the second is the mathematical, the quantitative approach, which you can use to identify that which are the best features. And now once you know this, once you're able to see that, okay, steeple width is not a very good quality feature, what you can do is you can now in the next iteration, you can drop the steeple width and rebuild the model. Okay, so the next iteration, what you can do, you can drop the sepal width column and you can rebuild the model without the sepal width column. And this is the experimentation part that we do in machine learning. We constantly try out different things. We try building different models, and we try to build the best model. So this is what we will do in the next iteration. Anyways, most of you are able to do this. So we are using a pipeline. I'm sticking to a basic logistic regression model, and I'm getting close to 96.67% accuracy. The answers can be different, and the reason why the answers are different is because some of you would have taken a different train test split. Your ratios would have been different. So if you're using a different training data, a different testing data, you will get a different answer. And we also discussed that it's not right to trust this single accuracy number, because the testing data set could be biased. It could be that the testing data is too easy or the testing data is too hard. So it is not right to rely on a single accuracy metric. Rather, we calculate multiple accuracies and calculate an average cross-validation accuracy. We talked about that. Now coming to the predict proba, we will have three probability values that will come out of it. Why? Because there are three classes. So first part is you build a model, and the second part is you use that model, you use the trained model to do predictions on the testing data. So we will use predict proba, and this time predict proba will return three class probability values to us. And what are the different numbers we are seeing right now? So the first one that you see is the probability of setosa. Let me write it down. This is setosa S. The second one is the probability of versicolor, VE, and the third one is the probability of virginica, VI. So what Python will by default do is it will typically sort your data in ascending order, and it will typically display your data in ascending order. So S will come first, then VE will come, E comes before I, and then VIR will come because I comes after I. So Virginica will come at the end. So this is the way Python will sort your data internally. Because remember, as per my data set, as per whatever data set I gave, I only gave the actual values here, Setosa, Versicolor, Virginica. So this is the way how it's sorting. And internally, in all the computations and all that it does, it will internally go and list out your data in this alphabetical order. Even later on, when we see the confusion matrix, there also you will see that the data will be listed out in a alphabetical order. Okay, so that's an important thing to keep in mind. So very clearly, the probability of setosa is 93.58%. What is this E minus 0.1? E minus 0.1 stands for exponential. It means 10 to the power minus 1. E minus 0.1 means 10 to the power minus 1. That is the meaning of E minus 0.1. Okay. So what is E minus 0.1? E minus 0.1 means 10 to the power minus 1. So that's the inference we can get out of it. So E minus 0.1 means 10 to the power minus 1. That's the inference we can get out of it overall. So very clearly we can say that. Okay, this is 90.93. 10 to the power minus 1 corresponds to 0.93, which means there is a 93% chance that this is setosa. There is a 64% chance that this is versicolor. Sorry, there's a 6.4% chance it is versicolor, and there's a very, very small probability is virginica. So whichever the probabilities are high, wherever the probabilities are high, the model will predict that. The model will predict that particular class. So that's the way how the default probabilities will go. But of course, you can keep your own thresholds and you can do it that way. Now, this was the confusion matrix. And as I told you, this was a new learning, especially for this exercise. We can see the confusion matrix, how it looks like. And very clearly, the confusion matrix tells you, it gives you a comparison between the actuals and the predicteds. Okay, so the confusion matrix will give you the comparison between the actual values and the predicted values, and this is the inference we are able to get. So we are able to see the actual uh, uh, the values, and we are able to see the predicted values. This is how we can understand the confusion matrix overall. Okay, so you can clearly make out the actual values vis-a-vis the predicted values. Okay, that's the inference you can make. So you can see that let me write it down. This is setosa, this is versicolor, and this is virginica. Remember, along the columns we have the predicted values, and along the rows we have the actual values. This is the order in which the data will be presented once again. And what is the benefit? The benefit is that you can look at these individual numbers and understand how the model is performing. So whatever model you trained on the training data, how is that model performing on the unseen test data? So you can see there are 12 such cases where the model predicted setosa and actually it is a setosa. There are 8 such cases where the model predicted. There are 8 such cases where the model predicted versicolor and actually it is a versicolor. And there are this many cases where the model predicted virginica and actually it's a virginica. There are 9 such cases. So you're able to very clearly understand how the model and how many correct predictions the model is doing. But what is more important is to understand the number of incorrect predictions. You can see. Okay, so now we can also understand the number of incorrect predictions. Okay, so we can make out how many incorrect predictions the model is making, especially the false negatives and the false positive part. So for example, you can see, and here we can see that there are this one incorrect prediction, because the iris one is a very good data set, because we already saw that the classes are very well separated. So there's very few incorrect predictions happening, one of which is this one, where there is one instance where the model predicted virginica. You can see the column total is virginica. So there is one particular instance where the model predicted virginica, but actually it is a versicolor. So that is the inference we are able to make. So there is again one particular instance where the model predicted virginica, but actually it is a versicolor. So that is the inference we are able to make once again here. Okay, I hope everybody is able to get a sense of this. So I hope the idea is absolutely clear. what this overall confusion matrix is, uh, you know, uh, uh, denoting. Okay. So this was about the iris dataset. Then we came to the next case study, which is the credit card, the default dataset. Again, it's a very interesting case study, very similar to what we talked about, very similar to what we covered. The ideas are not any different, but there were some new learnings that we had in this case study also, and some parts of it we discussed. And let me summarize it in a quick 5 minutes conversation once again. So this was my data set. Again, we have the different features of the customer, the limit balance, education, marriage, age, payment status, bill amount, past 6 months bill amount, past 6 months payment amount, how much payment you made against your credit card. It's a credit card data set, right? So you typically get a bill, then you make the payment for the bill. So this is giving all the typical transactional metrics against that customer's credit card account. Okay, so we're looking at the historical data, how the customer has used and interacted with the credit card account. Okay, how much bill he or she has incurred, how much payment he or she has made, what is the credit limit, what is the payment status, whether any late payments, did the customer pay on time. So these are all the different features of the customer that we have. And we also have default payment next month. So we also have a flag variable that we are using to track the default payment next month. That means we are saying that, hey, like this particular customer with today's reference point, we are trying to understand, will this customer default the next month? Next month is the month of June that will come. So we are trying to understand, will this customer default the next month? So that is what we are constantly trying to predict. So we already have a rich amount of labeled historical data. We have a lot of labeled data right now with us. So we have ones and zeros as per the labeled data that we have right now. And we are trying to figure out whether the customer will default the next month or not. That is what we are trying to do. So 1 means the customer will default and 0 means the customer will not default. So that's the inference we are able to get. So if you see the status, 1 means the customer defaulted the next month, and the status of 0 means the customer did not default or will not default the next month. So that is how the statuses look like right now. So 1 is you will default and 0 is you will not default. That's the inference. Okay. So we are trying to build a classification model based on this data. Okay, and I also told you that you should make it a point to drop these columns. ID column is obviously not important because this is not a good predictor of default status. Okay, a person's employee ID or any kind of identity features, these are basically serial numbers. Basically, these are roll numbers. So roll numbers have nothing to do with your actual default status, right? Row numbers have nothing to do with it. You should always make it a point to eliminate and drop these kinds of columns, and also these other columns like sex, education, marriage, because these kinds of features will contribute to bias. So whenever you encounter these kinds of features which have a potential to contribute to bias, you should always make it a point to drop these kinds of features. Otherwise, your models will end up being biased. Okay, so we did that. We did that here. Rest of the solutioning was very straightforward, and if you see, I dropped these columns and I went ahead and built a baseline model. This is some fundamental EDA I tried to do. You can see limit balance, for example. I'm looking at the distribution plot for limit balance, and you can see that this was part of an earlier conversation we had yesterday. We talked about histograms and skewness and all those beautiful things in the class. And if you recall, this is a right skewed or a positively skewed distribution. Okay, why do we call it a right skewed or positively skewed distribution? Because most of the limits are average to low. Most of the credit limits are average to low. And that is the general pattern, right? I mean, if you today take a credit card, most of the normal customers will typically get a credit limit of, let's say, close to 50,000 to 1 lakh. Normally, as a starter point, you might get a credit limit which is around that range. And there are very few customers who will start out with a very high credit limit. Okay, so it's inherently a right skewed distribution that we will find. Okay, so it's important to know this because I told you that supervised learning, when you're eventually building models using supervised learning algorithms, uh, the algorithms tend to function better, especially some of the algorithms tend to work very well when you're having more symmetric and more normal data. If you have skew in the data, the models will also have a tendency to become a little biased. Because if you see this case, we have lots of examples of customers who have average to low credit limit balance basically, and we have very few examples of customers who have high limit balance. So if you're thinking from a supervised learning perspective, you have a lot of data for average to low limit balance customers, but you have very limited amount of data for, let's say, high credit limit customers, high limit balance customers. So maybe we don't have enough patterns to for the high limit balance customers. So these are some of the limitations that we will have, and it's always a good practice to apply something called power transformer, which is what we will do in this notebook. Okay, so how do we reduce the skew? How do we take a right skewed and left skewed distribution, and how do we convert it into a symmetric normal form? So we go and use something called power transformer. So power transformers are what we use behind the scenes. Okay, which is exactly what we will do here also. And you can actually see this is a small demonstration what I try to do. So you can see this is the limit balance, the original distribution of limit balance feature, right, which is a right skewed or positively skewed distribution with high outliers. And when I go and apply power transformer, you can see this is the power transformation that I did, power transformer. These are internally mathematical transforms and all that we perform. So moment I do that, now you can see in the new revised data frame, the limit balance is more symmetric. Can you see? So the limit balance right now is more symmetric and more normal after we perform the power transformation. Okay, coming to the modeling part. The modeling part is straightforward. Most of you did it already, so I'm not going to take too much time here. So baseline logistic model, we're getting a fair amount of underfitting. And the interesting part I wanted to clarify is this one. This is the real takeaway from this exercise. As I told you, all these case studies, each of the case studies have some takeaways. Okay. Otherwise, the template is all the same. Do the train test plate, fit a model, get the accuracies, get the CV scores, build the confusion matrix. That's it. Work done. But what are the takeaways? What is the new learning from this exercise? The new learning from this exercise is this confusion matrix. If you look at it, although you're getting 70% accuracy, like, see, I mean, if I don't show you the confusion matrix for a minute, you will look at this accuracy numbers and say, hey, I think we have a decent model. I think we have a decent model, right? So we have 77% training, 77% testing. So we seem to have a very decent model. I'm not saying it's a very good model, but it will be like an average model, underfit model. There is always a scope to make it better. I told you that underfitting and overfitting are always relative terms. So there's always a scope to make it better. So here also we can clearly see that it's a kind of an underfit model. We are having 70% accuracy in training. We are having 70% accuracy in testing. So it's a kind of an underfit model. But there's a scope to make it better. There's definitely a scope to make it better. That's the idea. Now the interesting part is when you go and look at this in a bit more detail. So we are getting the predicted values here, lr.predict predicted values. We are building the confusion matrix. And once you take a look at the confusion matrix, now you start to realize that this is actually a dummy model. So this is actually a useless model. It's a dummy model. Although we are getting 77% accuracy, that 77% actually means nothing. And you know how and why we got that 77%? I'll tell you. I'll tell you how. So if I annotate, if I start the annotation for a minute, let me zoom in for a minute here. I'll zoom into the confusion matrix particularly. If I annotate, this is 0, this is 1, this is 0, this is 1, right? These are the predicted along the columns. These are the actuals along the rows. And if you look at it, the model is actually making no default predictions. So what you are seeing on the screen right now is a dummy model. It's a dummy classifier. This classification model is not making any zero predictions. Sorry, any default predictions. The classification model is not making any default predictions. This is a completely dummy model that we have on the screen right now. It is not making any default predictions. It is a completely dummy classifier. It's a completely dummy model that we have. So next time you get any test set, next time you're getting any test data and you're doing a prediction, all the predicted values are zeros. So mathematically, if there are total 6,000 records, because if you add up the numbers, you're getting total 6,000. Out of total 6,000 rows which are part of my test data, and if you do the maths, you actually have 6,000 records which are part of your test data. Out of total 6,000 sample test questions, all of them are predicted to be zero. The model is not making a single one class prediction. It's not even predicting a single record to be a defaulter. It's predicting all the customers to be not defaulters. See how useless the model is. I mean, this is in the context of a bank, a credit card. Now the primary objective of implementing this classification model in the credit card company was to identify defaulters. And look at this case. This is a case where it is not even identifying a single defaulter. It's by default saying everybody is not defaulter. Okay, all is hunky dory unless you see a big bubble building and finally maybe the company goes bankrupt because everybody starts to default now. That's the problem, right? So important uh, concept, important learning is that accuracy will not be a good indicator of the model performance. You need to do the confusion matrix to understand exactly what's going on. And you want to know how that 77% was calculated. This is your TP, right? This is your TP, this is your TN. That's your true negative, that's your true positive. If you remember the mathematics of the accuracy is nothing but Tn plus TP by total. I know the number is a little hidden, but this is actually 77.7%. So if you just do the maths right now, Tn plus TP by total, if you open up your calculator and do the maths, you will see the exact same number will come up, right? So if you do the maths right now, this is 4663. You can please open up your calculator and do the maths. You see 4663 by 6000. If you do this computation, you will get a figure which is exactly equal to 77.77%. That is how the accuracies are coming. So accuracy is not going to give you the full picture as to how the model is really doing. It is only the confusion matrix that will tell you, okay, this is how the model is doing against this class, and this is how the model is doing against this class. That's the concept, right? And this can be further uh, validated through the classification report, which is an extension basically. And in the classification report, you can also further see the support values. Support values are 4663, 1337. These are the actual number of records. So there are actually 46630 zeros. There are actually 13371 ones in the data set. And further, if you look at the classification report is going to give you what we call a class level accuracy. So not like an overall accuracy of 77%, but you can now understand what is the performance of each and every class without getting into the theory of precision recall and all that, which I shared in my conversation yesterday. But you can just focus on this metric called F1 score. At a very high level, you can look at F1 score. F1 score is like our new accuracy. F1 score is like our new accuracy, and you can think of this as the okay. This is how the zero class is on an average performing, and this is how the one class is on an average performing. So think of this as like our new accuracy metric. Okay, so you can clearly see that although the overall accuracy was 77%, but the moment we look at the class level performance, the one class is performing very poorly. Zero class is performing fairly well, but the one class is performing very poorly. And probably one of the reasons could be what some of the folks raised in the session. One of the reasons could be that because we have lesser number of records for the one class. We've got only 1337 records for the one class. So the data is highly imbalanced, due to which the model is finding it very difficult to understand the patterns for the one class. This is the cross validation that we did. And you can see now we are trying out different methods. We are applying power transform and then logistic regression. How will power transform help us? Where we expect that power transform will try to mitigate some of those extreme skews we have in the data. This is again part of the data pre-processing that we are doing. And indeed, by doing that, we are able to get a slightly better model. You can see the average CV accuracies actually become better. And in fact, when after applying power transform, when I rebuild the confusion matrix, well, I mean, you'll be surprised to see that this model is much better than what I had before. So this is what I mean by the incremental improvement. So initially, the baseline model was horrible. The one class was not at all performing well, but now you can see, moment I did power transform, the one class all of a sudden has started to do better. And further, if you look at the false negatives, this is 1027, right? This is the credit card default data set. False negative is very costly. False negative means model predicted you will not default, but in reality, you are a defaulter. That is how we look at false negative. False negative means model predicted you will not default, but in reality, you are a defaulter. So you are able to, in reality, you have a defaulting customer, but you are unable to recognize those defaulters. That's a serious problem. 1027 false negative is very bad, but this is still better than what we had before. So before we had 1337 false negatives, but now the next solution with power transformer, after we reduce the skew in our data, after we made it more symmetric, more normal, we have incrementally made it better. Can you see? Next, we are applying decision trees. I will talk a little about decision trees in the next conversation. I intend to talk what is it. So far we were just using decision trees. So far I just told you, hey, there's something called a decision tree. but we don't really know what it is. I'll talk a little bit about that in a while. And this is the hyperparameter of a decision tree. This is a better algorithm. And with decision trees, we are able to get even better. Can you see? 799. So the false negatives are reducing, and we are able to get an incrementally better and better model as we go along. The F1 scores are also very, very high. So previously the F1 scores were 35% for one class, and now we can see the F1 scores are 50%. So this is the incremental improvement I was talking about, right? And this is with gradient boosting classifier, and no doubt gradient boosting will give us even better results, right? Very, very good results we're getting overall. So this is how we implemented the solution for the credit card default data set. Now, next thing what we will do is we look at another similar problem. There are three very, very interesting and very, very real world case studies I will take up, starting with a very interesting case study on income classification. Okay, income classification. So let me share this Kaggle case study with all of you. This was a very real world, use case that was taken up by the uh, Costa Rican bank. And what they tried to do is they tried to apply machine learning in the social welfare space. It's a very social use case, and the objective is to identify, based on the different features of the household, which households are likely to, like, which are the poorest families, basically. Okay, you can see the Inter-American Development Bank is asking the Kaggle community for help with the income qualification for some of the world's poorest families. So it's a very good use case, and you can see that one of the primary objectives is to ensure that can we support and can we identify which are the families who are really in need of government help. Even today, if you look at many of the beneficiary programs that are there, the ration schemes and the cash transfer schemes, the direct beneficiary transfer schemes that happen, even to some extent, many of the social welfare schemes that are there, they are not perfect. They are very inefficient. And one of the primary reasons why they're inefficient is because the targeting is not correct. Oftentimes, you might target based on caste, you might target based on, some other local factors. But are you really using data science? Are you really looking at the net assets, the net liabilities of a person? And are you really identifying poor families based on that? You might end up giving lakhs of loan waivers to a person just because he or she is a farmer. But are you taking into account that even farmers can have tens of thousands of acres of land, right? And that's a reality. There are many farm loan waivers which happen, but are you really identifying the individuals who are really in need? You might end up waiving loans for farmers who like own tens of thousands of acres of farmland. Why? Because you are just doing the categorization based on the fact that they are a farmer, based on the occupation. Similarly, you might do a categorization based on somebody's caste, somebody's religion, which is very common in our country, right? So the point is, can we use data science to now look at the objective metrics? We are looking at the real living conditions of a person, not their other things. We are looking at the real living conditions. You can be a farmer, you can be whatever caste, you can be whatever religion. If you stay in a good house, if you have 5 TVs in your house and 10 air conditioners running, I don't think by no definition you're a poor person, right? So this approach, what they propose here is looking at the objective data. It's like somebody will go and visit your house. They will do a census survey. They will actually survey the household features, what kind of things you have, what kind of equipment you have, right? Maybe some satellite data will be collected, where your house is based, in what locality you are staying, right? I mean, I don't think you can say that, hey, you're living in HSR layout in Bangalore and you say you want government support. Okay, so that's a problem. You might be of some caste, you might be a farmer staying in Kormangla in Bangalore, or you might be a farmer staying in upscale Bandra in Mumbai. And then what do you need? You need government support. That's a problem. Why? Because the satellite imagery will pick up that, okay, this is Bandra. This is one of the most, let's say you're having a property in Jubilee Hills and you want government support. Why? Because you're a farmer. So what this model will do is it will identify several factors. It will identify the location where you live. It will look at the median housing prices in that location. It will look at your house where you live. It will look at the observable features in your house, and based on that, it will predict that, hey, are we, are you rich or are you poor? This is the data set, just to give you an idea to all of you what kind of data we have here. You can see the target column, as was proposed here, was grouped into 4 categories: extreme poverty, moderate poverty, vulnerable households, and non-vulnerable households. So these are total 4 classes we have right now. So this is what we are trying to predict. And this is the output column, and these are the features of the house. I told you that we are looking at the observable features of the house. So we are looking at features like number of tablets in the household. And how is this data collected? Even this is important, right? You might be wondering that, assign, what is the guarantee that this data is collected correctly? And that's a very good point. That's a very good point that you raise, because if your data is not right, nothing we are discussing makes sense. Nothing we are discussing will add up if your data is not right. And this goes back to all our discussions we have had so far. We are trusting on our data. Your data has to be correct. See, if you're sending people in your house to do a survey, and you give them some money, and you ask them to enter wrong values, then anyways anything will get corrupt. So operationally, you have to make sure that you collect your data properly. We are trusting on the fact that if you collect your data properly, if somebody, maybe there'll be some monitoring mechanisms you can check up. I mean, it maybe this entire process will be video recorded, and there are a lot of ways it could be done. Ground level operations is a very different challenge altogether. Maybe we can look at some kind of video based manner. Maybe somebody will wear like a GoPro device, they'll enter your house, they'll look at your features, and maybe use a computer vision based model, image processing model, to identify what kind of house you're living in. And we have the capabilities, we have the technology to do that. Actually, a powerful computer vision model just needs a 360-degree picture to model your entire house, even to the level of detail, to the kind of materials you're using in the floor. It's not like a normal floor, but it's a very posh set of tiles you're using, or let's say a carpeted floor, like uh, and that'll tell a lot about the kind of the wealth of the family to some extent, right? Anyway, so if the household has a refrigerator, do they have a bathroom, how many tablets are there, how many males are there? These are some demographic attributes in terms of age. What is the average age of the household? Years of schooling. You're trying to understand something about the education level of the household. The size of the household is an important factor, because it's a very big house, then that's another thing, right? So why is it important? Because you're trying to somehow correlate the size with respect to the total number of persons. Okay, I think if it's a rich family, then the more the number of persons, the bigger the house. And if it's a poor family, I mean, despite having a lot of people, the size is still very small. A lot of people are cramped. So this is a very good indicator in terms of the family wealth, in terms of, okay. We're also looking at factors like what is the material used in the wall, what is the material used in the floor. This is what I was mentioning. You can take pictures and predict that. Okay, and how is the electricity coming? Toilet. Okay, source of energy. This is actually very important. Okay, and this could be a very interesting factor to for poverty prediction. What is the energy source for you are using for cooking? Is it electricity? Is it gas? Is it charcoal? So if you see that somebody is using wood and charcoal for cooking, I think that's a very clear indicator that the family is not well off, because they cannot afford electricity, or maybe they stay in a place where there is no current, where there is no gas that goes, or maybe that's too costly. Cooking gas is too costly, so they're still using wood charcoal for cooking, although it's very unhealthy and it's very unsafe. Okay, so these are some very important factors we are seeing: wall quality, roof quality, uh, some demographic factors, things like that. Lots of features we are looking at: the region where the house is located, how many TVs are there, does it have a TV, does it have a laptop, does it have a mobile phone, right? And based on all these features, these are all X's, right? You can see there's close to 100 odd features we are tracking. And based on all these features, we are trying to predict uh, the kind of poverty level of the household. It's a multi-class classification problem. Why? Because there are 4 classes we are trying to predict. Okay, and again, we will have historical data. We would have collected the data from, other families. Historical data we would have collected. And based on that, next time we come across a new family in a new area, we will look at their features and say, okay, are you rich, are you poor, or are you what class you belong to? That is the key takeaway. One more very interesting point I would like to highlight. If you look at these 4 classes seem to be overlapping to some extent. Okay, so there are 4 classes, but they seem to be overlapping to some extent. Okay. So if you look at extreme poverty, if you look at moderate poverty, and if you look at vulnerable household, all three are poor, right? Now, all that we are trying to do is we are trying to identify the degree of poverty. And remember, this is a very hard problem. Okay. So identifying the degree of poverty is a very hard problem. This is a very hard problem that we are trying to solve. Why am I saying this? Why am I making this statement? The reason is because, the reason is because, if you see, the reason is because there will be a lot of cases where model predicted extreme poverty, but actually it will be moderate poverty. Think about it, because we talked about confusion matrix, right? So what are the steps involved? First step is you take the data, the training data, and you build a model. And after you build a model, you will evaluate your model against the test data. Just how we discussed, we will create a confusion matrix and we will try to evaluate the model against some test data. Okay. You will find a lot of cases where model predicted vulnerable, but I'm sorry, model predicted extreme poverty, but actually it is moderate poverty. You will find a lot of cases where model predicted moderate poverty, but actually it is vulnerable. But if you think about it, they're all poor, right? It is able to classify the poor part correctly, but what it is not able to classify that well is the degree of poorness. And this brings us to a very important discussion in terms of framing the problem. So you need to now decide uh, from a business perspective, from a government perspective, like, is it important for the government to decide the level of poverty? Even now, a lot of the direct beneficiary transfer schemes, if you see, they're just classifying it in a binary manner, right? Is your income falling below this threshold? If your average income is below this threshold, then you are considered to be poor and you need government support. Yes or no? Like that. You don't really need four classes. And conceptually, this is the concept, okay? Conceptually, the more the number of classes you have, the lesser the accuracy and the more the errors you will end up making. You will end up making lots of errors between those classes, like the one that I discussed. You have a lot of cases where model predicted extreme poverty, but actually it is moderate poverty. Model predicted moderate poverty, but actually it is vulnerable, or vice versa. Model predicted vulnerable, but actually is moderate. But they're all oscillating between the same poor category. So what we can instead do is a sure short way to increase the accuracy of the model. A sure short way to increase the accuracy of the model would be to group these three categories and call them poor, and to group this category and call them rich. Okay, something like that. Very simple data pre-processing we can do right at the outset when we start solving the problem. We can convert it to a binary problem, because binary classification is inherently easier to do. Even accuracy wise, you will get a slightly higher answer, a slightly higher accuracy if you're doing binary classification. And it's quite obvious, right? I mean, it's conceptually quite obvious because it's an easier problem to solve. You are either saying, hey, are you rich? Are you poor? It's a lot easier to do. But within that poor, if you're trying to classify that, hey, these are the three different categories of poor, tell me exactly what category it is. The more the number of classes you start adding, the more difficult the problem becomes. And the harder it becomes. And obviously, you will find a big impact on your accuracy metrics. So that is the other thing that you will. So these were some of the key ideas that I wanted to clarify in this exercise. You can go over it. The complete solution is shared with you. I have also shared a very interesting reference paper, in the Indian context, measuring poverty in India with machine learning and remote sensing. This is very interesting because what they are doing is they are not only looking at the census data. This was from the Costa Rican, use case, which I've shared the solution file for. This paper is in the Indian context. And here we talk about the kind of data and see, very interesting. Not only are we taking into account the census data, the census data is the one that we discussed, right? So data from the census survey. You send people to the homes and you will, find out the observable features and all that. Not only are we getting the household data, we're getting the material living conditions, right? This is something we talked about, but we are also trying to get data from satellite imagery. Very interesting. We're getting satellite imagery data and we're getting nightlight data. Now, what is the importance of these two things? Well, nightlight data will tell me about let's say if you're taking a picture of an area at night, if you're looking at a satellite image, like, you would have seen some of those NASA images, no? Sometimes they come up with those beautiful pictures of the Earth, how it looks like uh, at night. And you will see that the major metro cities, right? I mean, if the area is more developed, like I'll take an example of Bangalore because that's what most people can relate to. If you go closer to Bangalore, or if you're, let's say you're taking a flight and you're landing in Bangalore, you start to see that lots of lights will start to come up, right? That means there is more electrification. That means in that area, in that 100 square kilometers or 1,000 square kilometers, area that you see, there is a lot of electrification. That means there's a lot of development. And as you start moving away from that area, you will see that the places become less and less developed because it becomes darker. There are not too many lights. And maybe as you get towards the villages, the outskirts of Karnataka, right? I mean, it's not Bangalore. Everything is not Bangalore in India, right? So as you go towards the outskirts, you will see that there is no electricity. There are still villages which have only few hours of power that come in a day, and there are a lot of blackouts that happen. And if you look at it, that's a very good indicator of development. Okay, so the nightlight data will also be one of the features that will be used to identify the level of poverty in the household. So we will look at the observable living conditions, like the thing that we talked about. We will look at the nightlight data to make a sense of the area as a whole, the locality as a whole, right? And try to make sense of the wealth of the household based on the locality. We will look at the satellite imagery data. Satellite imagery can give us other very interesting metrics. So satellite imagery will tell us about the area, and maybe in a 100 square kilometer radius, 100 square kilometer radius that we look at, we can track that, hey, 100 kilometer area that we see, we can basically track how many hospitals are there, how many parks are there. Okay, what is the road infrastructure that is there? So you can even look at a Google Maps, and you can look at a satellite imagery data, and based on where your house is located, you can find out all these factors. So what I'm getting at is, in a real world project, right? What is the analogy that I'm trying to draw? The analogy that I'm trying to draw here is, in a real world project, data will typically come from multiple sources. So data will not just be a single CSV file, which, like some of the exercises that we have worked on. You will not get like a single CSV file and build a model using that. No. So in the real world, data will always come from multiple sources. So data will come from different sources, and that's the key takeaway. That's the key takeaway that I wanted to highlight as in here. So here also you can see that there's some data coming from the census data. There's some data coming from the nightlight data. There's some data coming from the satellite data, and the objective of data pre-processing would be to join the data from all these different sources, create one single consolidated data set, and then work with it. Okay, and this is also a very important part of what you will do in your projects going forward. On the same lines, I've uploaded one more very interesting case study, which you can go for it later on. This is also something related to a credit card use case. I've given the solution file for it. You can see this later on. But this is also related to the same concept. How in the real world you will go and you will use data from different sources, right? So just to give you a little bit of basic idea about this data set, we have got two different CSV files. We have a credit record.csv file, which is giving us information about the customer's credit card usage. And we have an application record.csv file, which is giving us information about the credit card applications. So let's say you apply for a credit card. So we have some information about you. Okay, you apply for the card and we have some information about you. Okay. And what we are trying to do is, uh, we are trying to build a model to predict whether the card should be approved or not. The use case that we discussed a while back was default. You are already a holder of a credit card, and we are trying to predict next month, will you default, will you not default? So the use case is very different. There, the use case was different. There, we were dealing with existing customers. I'm a customer, I'm using my credit card a lot this month, let's say. Now, my bank is trying to predict what is the probability I will default. Okay, I rack up, let's say, 2 lakh rupees of expenses this month. So next month, I simply just vanish away. I vanish away without paying my dues. That is what the banks are trying to predict for existing customers. This is where you're looking at a credit card application workflow. This is what happens when you apply for a new credit card. It's a very common use case. Okay, very common use case. Even today, when you go to any bank and you fill up the credit card form, you will see that they take a lot of information, right? They will ask you for your last 3 months salary slip, and which is very standard procedure because the banks are trying to understand your income. And credit cards, like except for the free credit cards that you get, many of the premium credit cards, if you go for, this is a very standard operating procedure, okay, where they will ask you for your last 3 months or last 6 months salary slip. They will ask for your bank statement just to estimate your net worth, because they want to be sure that if they are giving the credit card to you, they want to be sure that you are somebody who can afford to repay. Okay, because otherwise, if it's a very high credit, and this is also used to identify the credit limit, and a lot of machine learning is getting used here, right? And this is exactly the use case we are discussing. Oftentimes, you will see that, okay, the bank will reject the card. So then you will go to your relationship manager and ask, sir, what happened? What happened? And their usual answer will be, sir, I don't know. The backend team has denied. So whenever they are saying this kind of thing, the backend team, operations team has denied the card. Your RM and your bank and your branch manager knows nothing. They're not technical people, right? There is an algorithm, there is a process, there is a classification model that is built, and the operations team, for the backend team, they will look at your application data, where you are living, what is your income, how many dependents, everything they will look at, and they will predict that is this person, should it be approved, should it not be approved. That's it. Straightforward, yes, no answer. Okay, there are no reasons and all they will tell you. It's just a straightforward classification. That is the use case we are discussing here. Now, important thing is we cannot work with two CSV files, right? If you look at this particular use case, we cannot have two CSV files. All the data sets that we have worked on so far, we need a single file. We need a single table, a single data set, right? We need one X, we need one Y. We cannot have like two different CSV files. But this is what the real world scenario will be. When you're solving these problems in the real world, you will work with multiple files. You will have different CSV files that you will have to work with. So what do you do in that kind of a scenario? If you have multiple CSV files, what do you do? So you will have to figure out a way. You will have to figure out a way to join the data. So now the onus is on you to figure out how do we go and join the data effectively? How do I take the data from all these different sources? So how do I take the data from all these different sources, and how do I join the data effectively? So please keep this at the back of your mind. This is very important, right? And it's very normal for in data sets, especially if you're working with SQL databases, relational databases. You might have 7, 8 different tables, right? You might have a normalized schema, and you might have 7, 8 different tables that are used in the particular problem. So you will have to join all those tables. Okay, so before you build a machine learning model, you remember that you need a single data frame. You need to have a single table with some X, some Y. Your algorithms cannot run on different tables. Okay, so this is again something that has to be done as part of the pre-processing. You have to convert everything into a single table. You have to convert everything as part of a single data frame. And that is going to be part of the logic that you will have to write going forward. Okay, so there are two other case studies that I will be talking about right now. In fact, there is one other case study, which is a very, very interesting one, which is the lead scoring case study. Okay, a slightly different use case. But while I discuss this case study, I will pause for a minute and I will ask each and every one of you to go to the lead scoring case study folder and just read through the leads.csv file and the leads data dictionary file. All right, so first we'll start our discussion with the leads scoring case study. And it's a very interesting use case. It's a very interesting use case, something which is a little different from all the typical classification and regression use cases that we have discussed so far. So this is a very, very interesting use case where we are trying to look at the different features of a lead, which is a prospective customer. A lead is basically a prospective customer. So you are looking at the different features of the lead, and based on that, you are trying to predict whether a lead will convert or not. So that is the overall objective of what we are trying to do here, right? So what is a lead? What is the meaning of a lead? So imagine you want to buy something. You want to buy something on, you want to buy a shampoo, or let's say you want to buy a course, or you want to buy a car. So the moment you want to buy something, you are a prospective customer, right? You are a lead. So from the company's perspective, you are a lead because you went to the company's website. Imagine you are trying to buy a shampoo, a very high end. Let's say there's a company, a small company on beauty products in India called Minimalist. The Minimalist actually sells all these, face serums and all that. If you know about the company, so let's say you're interested in buying one of their products. So what you do, you go to their website, and you spend some time, you spend 5 minutes and you browse through the different products, what kind of products they have, you look at the descriptions, you look at the reviews. Let's say you call up their customer care and you're really interested to buy some of their products to try them. Okay, so the moment you do that, the moment you take these initial set of steps, you become a prospective customer, you become a lead for the brand. They are trying to sell something, and here you come, you're a customer who somehow discovered them. Maybe you discovered the company through some Google ads or through some kind of affiliate search links, and you are able to land up in their homepage. The moment you do that, the moment you call up their customer care, you become a lead. Okay, and now what the company is trying to do is they are trying to predict that what is the probability that you will convert. What is the probability that now you're a prospective customer, you're a lead, you're just a lead, just a prospective customer. It's like you're a window shopper. What is the possibility that you will actually end up paying for their product? That's the problem that we are trying to solve. So can we use machine learning to estimate that based on the different features of the customer? It could be something as simple as the amount of time you spent on the website, or let's say when you call up the customer care, how much time you spent on the interaction. So can we look at all these features of the customer, and can we predict how much time it will take, whether the customer will convert or not convert, whether you will end up converting into a paying customer or not? So that's the objective that we are trying to address. Now, what I will do is I'll take you to this, to this beautiful use case. This is just to show you a slightly visual, a picture in terms of what is going on, right? So whenever we are doing anything in machine learning, it is very important to relate to the big picture. Okay, what is the big picture? How things were before, how things were before we did ML, and how things are after we implemented machine learning in the process. And there has to be real business benefits, right? So if you think from this perspective, let's say we have uh, a typical call center, outbound call center operation, where uh, there's a person who will, like in the beginning of the day, what happens is they will do some very basic analytics. They will collate the data from different third-party, data collection agencies, and this is like your typical, Bajaj Finance and all those kinds of companies. I'm not naming anything in particular, but you get like many of these spam calls through the day. Right? Somebody will randomly call you and say, "Sir, you want a personal loan? Sir, you want to take this collection? You want to buy our product?" Some random messages we will see, right? So they'll say, "Okay, we are offering a plot of land for some lakhs or something." Okay, so this is like, what you call as cold calling. Okay, I didn't even ask for the call. I don't even want to purchase something, but somebody out of nowhere ends up calling me in the middle of my busy hours, and they are wasting my time and their time because you are not even a customer interested to buy something. So much of the outbound calling and the calling that happens today is very inefficient, and I'm sure you agree, like it's very inefficient because the data that these guys have, it's not to blame them, right? They're given a piece of paper and they're given 100 numbers and said, okay, call them. And the targets are completely based on that. But it's a very inefficient process because the data that they have itself is very stale. Maybe some 10 years back, you would have taken a loan from some third party, NBFC company. And because some 10 years back you took a loan, the company thinks that maybe you need a loan today. That is not updated. So, just because they have you in their database, they think that you might have, you will need to take loans all through your life. But they're not really looking at your real-time data in terms of your bank statements, in terms of your net worth. Do you really need a loan? Or maybe you're a person who wants to give a loan now. So are we really taking that into account? Maybe not. So this is the traditional process I've highlighted here. So start of the day, you get 100 leads. 100 leads are 100 potential customers who you need to call. And your team lead tells you that, okay, pick up the phone, call up these 100 customers, and approximately you're spending, let's say, 5 minutes per lead. Okay, some people will talk to you nicely. Some people will say, hi, hello, keep the call in 2 seconds. Right? So average, let's say we are spending 5 minutes per lead. Okay. Now, because the process is very inefficient, you end up getting only two converts. It's a very inefficient process, and because of that, you end up getting only two converts. That's the problem. So look at the amount of cost. Look at the cost of the process. So you are effectively spending 500 minutes, right? 500 minutes is a lot of time, right? So 240 minutes is 4 hours, right? So 480 minutes is 8 hours, right? 8, huh? 8 hours. 8 hours, approximately 8.5 hours you're spending to complete these calls. And in those 8 hours, like the whole day that you spend in the call center, you end up only converting two customers. So much of effort you put in, right? And mind you, those 8 hours are not free. Of course, you are getting paid, but from the company's point of view, they are having to pay you for those 8 hours, right? So they are incurring a very high cost, right? Of course, we can debate about the cost and the cost structure, but whatever, they're paying for no reason. They're paying for a very inefficient process. They're paying you to make 8 hours worth of calls just to get two converts. And all the convincing, you will talk to the customer, say this is a great product, please buy, and somebody eventually buys. Now, what are we trying to achieve here? This is how it used to be. And obviously, from a slightly technical perspective, you can see there are lots of like so-called false positives. Okay, so this is a process that is very inefficient because there are lots of FPs, false positives in this manual process. There are 100 leads that you're getting in the beginning, which means that somebody thinks that these 100 customers will convert. These 100 leads will convert. So there are 100 predictions that you're making, but you end up getting only two converts. So there are 98 false positives. That's another perspective of looking at things. So this process right now, as we see, there are 98 FPs. So there are 98 such leads which you think will convert, but in reality they're not converting. Because see, you are calling the customer only because you think that they will convert. Otherwise, like why will you call, right? So you think that they will convert. So the manual model that we were using before, there are 98 such predictions where you think the customers are good and they might, sorry, the leads are good and they might convert, but in reality they don't convert. So there are a lot of false positives, and that is what makes the process very inefficient, right? So a lot of false alarms are playing out. Now, how will machine learning solve the problem? So we are trying to implement a workflow that looks somewhat like this. Now all of you can see the screen. Now we have the same 100 leads, but this time the agent will not directly pick up the phone and call the customers. They will not directly call up the leads. It will first pass through a machine learning classifier. The classification model will assign a probability of whether the customer will convert, whether the customer will not convert. So it is like a predict proba. So instead of directly calling up the leads, you will pass it through a classification model, and using that we will find out what is the probability of convert. And then we will use a conditional if else statement and say, hey, if that predict proba is more than 30%, 30% probability of conversion is extremely high in sales and marketing terms. So if we have a 30% chance of conversion, that means most likely these leads will definitely convert. So you will send it to one set of salespeople who are proficient in handling those kinds of end processes. So they are the ones who will, let's say, be ready with the documentation and other things, and they will not have to like spend much time in convincing the customer. So these folks will make the transition process very smooth. So you can directly buy the product and the documentations and contracts and everything, and they get free contracts, converts in the process. Okay, so there are like six of these leads where the probability of conversion is between 10 to 30%. Okay, and this set of leads we will send to another group of this set of leads we will go and look at another set of salespeople, and there is another set of leads where the probability of conversion is less than 10%. So we have a less than 10% chance of conversion, and because we have a less than 10% chance of conversion, so 90 of these leads are like that. So there are 90 of these leads where the probability of conversion is less than 10%, and because it is less than 10%, there's almost like no likelihood of conversion. So you discard these leads. Now we can debate about these threshold values. I'm just taking a ballpark number, but typically in the real world, this number will be much lower, because even if you have like a 1% chance that a lead will convert, you still want to take a chance and call the lead. So maybe this number will be as low as 1% in practice. So only if it's less than 1%, only if the probability of conversion is less than 1%, only then you will discard the leads. Because when you discard a lead, you have to understand that you're straight away losing business. So before you discard, you want to be very sure. You want to be very, very sure that, hey, I think this customer definitely will not come with us. So in other words, you can say that the false negatives are very costly, especially for this particular problem statement. False negatives are very costly. Model predicted you will not convert, but in reality you convert. That is absolutely unacceptable, because the moment you have a false negative, you are straight away making an upfront loss, right? So whatever be the cost of your product, if it's especially if it's a very high value product, imagine you're maybe just giving an example, you're selling a car. Now, obviously car sales channels may not be like this. I'm just taking an example. Maybe let's say you're selling a course. online education technology edtech course you're selling, some of these courses or the degree programs can go up to 2.5, 3 lakhs, right? It's a very high value, product or a course that you're trying to buy, and a false negative can be extremely costly. So the classification model predicted the lead will not convert, but in reality it did. So that is unacceptable. So FP is still fine, FP is still okay, but FN is not acceptable. So that's why the thresholds will be, we'll try to put it as low as possible. Okay, but this is still a much more efficient process, right? This is still a much more efficient process than the above one, because we are able to. So for the company, it is like a win-win. It's a win-win for everybody. For the organization, it is like a win-win. So the organization ends up spending less money, so the cost is lower, and it also ends up getting more converts, so the revenues are higher, right? So if you think of discarding these 90 customers out of 100 leads, you're straight away discarding these 90 leads based on your thresholds. So you only end up with net 10 leads, and those 10 leads you're getting 5 converts. So you can see that you're only effectively making these 10 calls and you're getting 5 converts. Why? Because you're channelizing it better. That is the other benefit of using machine learning for defining a process flow, because you're able to channelize those leads better. So the same person, the same call center operator is not handling all the customers, but in this case you're finding out what is the probability of conversion, and based on that, that is given to different customers, right? So this is the way how you can streamline customer support using machine learning, which is, we are seeing a lot of that happening today generally. So another simple example could be, maybe the use case is more aligned with text data, but let's say you buy something on Amazon and you're very unhappy with the product or service. So Amazon has something called the customer chat feature. You don't need to necessarily call them. You can directly chat with them. And a lot of these kinds of models can potentially be leveraged. Okay, I'm not saying that they are exactly being leveraged, but I'm saying there's a huge potential where, let's say you directly start out saying that, okay, I'm very unhappy with the product. I bought this yesterday and this item was missing, or this product seemed to be secondhand, and you're very frustrated. So you write, let's say, 3, 4 paragraphs, and in the chat, there is some kind of classification model that is being used. Okay, there is some kind of classification model we are using behind the scenes, which is looking at the text message and it is trying to predict the sentiment of the user. So based on the message, it is trying to predict the sentiment. And if it predicts a negative sentiment, if the sentiment is negative, maybe that chat will be automatically transferred to an escalation panel. Okay, if you're not that agitated, if you're not that negative, if it's a moderate or a neutral sentiment, then it will be sent to the regular process flow. Okay, so these are some of the ways how machine learning can also be used for, for channelizing the different cases and channelizing the workflow in a better way. So if the probability is higher, if the probability of negative sentiment is higher, we'll send it to an escalation team. And if the probability of negative sentiment is lower, if it's a positive sentiment or a neutral sentiment, then we'll send it to the normal flow. Okay, so there are a lot of potential avenues how this can be leveraged. So now coming to the exact exercise, this is the leads data set we have. So that's the leads.csv file, and you can see this is the real data. Every single row corresponds to a lead, and we have the different features of a lead. Okay, so you can see every row corresponds to one lead or one prospective customer. So we have the origin, the lead source. These are the different features: total visits, total time, lead activity, country, specialization. So all of these are the different features of the lead, and on the basis of that, we are trying to predict the converted status. See, there's a column called converted, and this is what we are trying to predict. Okay, so converted can be either 1 or 0. Okay, now you might be wondering, how is this data even coming? Where is this data coming from? This data is coming from the historical context. So what you are seeing on the screen is purely historical data. Okay, so this data is coming from the historical context. So you already have a lot of data available for past customers, and you know that leads like this, right? So somebody who was, let's say, browsing the website for a long time. So leads like this are more likely to convert, whereas leads like this are less likely to convert. So you already have this data from the past historical context. You have studied the marketing campaigns over the last 2, 3 years, and this is how marketing campaigns go, right? You uh, you advertise your company or you advertise your product on Google or different marketing platforms, and you see the inbound visits that are coming, how many customers are coming to your site, what is the conversion ratio. So that is how you collect your label data. That is how you collect your XY combinations, right? And once you know that, okay, leads like this they converted and leads like this they did not convert, once you have that historical data, once you have that label data, now you can build a classification model. Okay, and the other things we will follow the same way, like we do the pre-processing, feature selection, all those are part of the process. But now you'll build a model, and next time you have a new lead, next time you have a new customer, you will try to predict whether that customer will convert or not convert. So based on the historical data, you build a model, and next time we have a new lead or a new customer, we will try to predict whether the lead will convert or not convert. So that's the way how we are looking at it. So this is the data dictionary where I've defined the different features, and all of you, you had enough time to go through this already. And here we have actually solved the problem. If you see, this is the notebook where I've already shared the entire end-to-end solution. So this part is easy, but the core objective of this exercise, the new learning, the key learning that I wanted to discuss here was just a case study, just the business aspect of things. Okay, so whenever you're doing machine learning, don't just try to focus on the technical solution. The technical solution is in many ways easy. You have a data set, you know X, you know Y, you have all the methods in your repository. That's the easy part. But your projects will not even start. Your projects will not even get funding from the stakeholders if you are unable to justify the value of machine learning. So in many ways, that part I would say is far, far more important, where you have to define the value. You have to explicitly state what is the value that the machine learning project brings to the table. So that's a very, very important thing to basically keep in mind. Okay, in this case, there is a very clear value that you can justify. You can say that, okay, we have managed to, by implementing machine learning, we are able to uh, achieve a very high return on investment. So initially there'll be a cost to set up the solution. You have to hire a team, you have to set up some hardware. So all of these are specialized tasks which need some initial cost. But if you can justify the returns on investment, if you can justify the cost reductions, then that part is also very, very important in ML. Okay, so even in the whatever be the business domain, it could be a healthcare use case, it could be a networking use case, okay, it could be a data center use case. There are huge benefits that you can actually cite in terms of how machine learning actually helps. Okay, okay, so this is pretty much the solutioning we have done. And otherwise, I think after we have done the data pre-processing, this part is the normal approach that we followed. We are trying out different models. You can see we start out with a decision tree, and the decision tree we are getting around 80% and 78% accuracy. And I told you false negatives are very costly. The false negative means model predicted you will not convert, but in reality you do convert. So FNs are very costly. And this is the hyperparameter tuning that we can do. So with respect to a decision tree, we can tune the maximum depth hyperparameter. So if the smaller the value, the more underfit the model, and the larger the value, the more overfit the model. So remember, I told you on the first day that different algorithms will have different hyperparameters. Okay, so all the algorithms will have hyperparameters. Different algorithms will have different hyperparameters, and you have to tune the hyperparameters. You have to find exactly the right value of the hyperparameter. So that is the tuning that you will have to do here. Okay, and I think the good fit zone is coming somewhere around here. So when depth is equal to 6 or 7, I think this is where the cross-validation score is coming out to be the highest. So the overall accuracy, the testing accuracy or the validation accuracy is coming out to be the highest somewhere around here, 80%. So this is where we can say that we have the best model. So the depth of 6 or 7 is ideal. Okay, because if I have a higher value of depth, then beyond the point, the training score continues to become higher, whereas the testing score continues to fall. So this is the overfitting that is happening. So, and relatively, the model is becoming more and more overfit. Okay, that means on the training data, whatever textbook you have, it will do very well. But in the unseen question paper, it is starting to do very, very poorly. So this is what we can do. And now we are trying out different models. We are trying out a random forest. We are trying out different models to, improve the scores. Okay, so this template will be very similar. But I think what is very important whenever you start with any exercise is to have a very strong and very robust overall understanding of the benefits of the benefits of machine learning. What is the business problem that you are solving? That is very, very important. So now I will take you through a few algorithms, a few different types of algorithms that we have broadly talked about, right? As I told you right on the first day, the agenda is not to teach you theory. We will not be getting into individual, names and try to give you, bore you with all the math and the theory, because honestly, from an application perspective, it really does not matter. Okay, so that's another level of learning. That's another track. That's another career path where you try to uh, understand the math behind the algorithms. But here we are trying to focus on applications. At the same time, we want to strike a balance. We want to strike a balance so that some of the most important algorithms you at least know, at least you understand. And with this in mind, I will recap this. I'll summarize this for you. But before that, let me quickly take you through another very, very popular algorithm called decision trees. Right? There's a lot of content I've also uploaded. This is some of the stuff I did from the first day. I hope you've seen this. This is the data science uh, cheat sheet I've uploaded. This is the data science project lifecycle, right? So pretty much how we go through a data science project, the different steps that are actually involved, right? So we have a so first thing that we try to do is one of the most important parts and a big part of what we did today as we went through the different case studies. I think you can all relate to this diagram a lot better in where we stand today. So first we do data discovery. We define the problem statement, right? I know it sounds very cliched, but it's very, very important. You have to define the problem statement correctly, because if you do not define the problem statement correctly, everything downstream will go for a toss. Because you have to be very clear, what are you trying to solve? Are we doing regression? Are we doing classification? Uh, because only when you define the problem statement correctly will you know what kind of data is needed, right? So the data requirements are also very, very important. So this is the first thing that we are doing. We are trying to define the problem statement correctly. And then we try to identify the different types of data sources, what type of sources are there, how do we connect to the different types of sources. This is the part where you will do the pre-processing, what I was mentioning, right? You might have a data from multiple different sources, and you will have to figure out a way to join them. You will have to figure out a way to combine the data coming from different sources, right? So next phase, after you ingest your data, because data will come from different platforms. It could be CSV is a very common file format that is available in the web. Any system that you are using, CSV or comma separated value is a very popular file format. From anywhere you can export to a CSV and you can work with it, which is why in data science projects, CSV is a very, very popular file format to work with. And you have to understand, like a lot of times people ask this question that, okay, what about working with real-time data? You have to understand these are static models. Okay, so all that we are trying to do, we are trying to take the data that is available until a particular point in time. Okay, if you're trying to, let's say, work on something in your project, okay, you have to take some static data, because every minute, every second data is getting generated. Okay, so the traditional machine learning that we are talking about here, you cannot work with dynamic data. You have to have some data available in a static file like a CSV up to a point in time. So let's say you say, hey, I have data until yesterday. So yesterday 12 midnight, I have data available, and I will use that data to do my development workflow. And now your development sprint starts for 2 weeks. You take your data, clean your data, build, try different models. Okay, but all of what you're doing, remember, is from data that you collected latest as of yesterday. Okay, so that is why whenever you're training machine learning models, it is very important, and even in your documentation, it is very important to state what kind of data you have taken. Okay, and what is the overall uh, recency of your data. If I have to relate it to something, like all these GPT models or the language models that we tend to use. Okay, so in all these language models, also you will find something very similar. Okay, so let's say, for example, if I look at the GPT model, right? So I can give you one example. I can give you one example in terms of what I'm trying to ask here. So yeah, this may not be so relevant for now, but just so that you can relate to it, that all the models that you're building, be it machine learning, be it deep learning, be it generative AI, all the different types of models, you will have a certain, uh, so you'll have a certain overall, recency, and you have to specify explicitly, what is the recency? What is the recency? You need to explicitly specify that. Okay, and that's an important thing to overall keep in mind. Okay, so until what time was my data available? Okay, so what I did is I went to my Azure portal. Okay, so these are things I'll teach you later as we go along in the session. So you can see that I have a I have a GPT-4 Omni model that I've deployed. So don't worry about these things right now. So this is not Chat GPT, but this is actually the development interface inside Azure. And what I wanted to show you is, let's say if I ask a question, who is the current US president, right? So if I ask, who is the current US president? So I mean, obviously, what are we doing here? So we are using behind the scenes, we are actually using a model which is called so so behind the scenes, we are all using a model which is a GPT-4o model. And you can clearly see the version is 2024. So this model was released in 20th November 2024. This is the version of the model. That means that means the data that OpenAI used to create this model, because this is also the ideas of machine learning are very similar. Although this is something else we are doing and all that, but the core ideas are still the same. You take some data, latest as of 2024, and using that you build a model, right? Using that you train a model. They would have taken a lot of time to train the model based on the data that they collected as of that day. And now what we are doing is model prediction. So I will type a prompt. And this is now hitting that deployed GPT model that is already trained. Okay. And what is happening? Model.predict. So this is like the X. GPT.predict will happen, and we are getting the Y. This is pretty much the workflow that is going on in a typical large language model, right? Think of it that way. Now, if I ask this question, you will see that I'll get a response which says it's Joe Biden, right? Look at it, and this is very interesting, right? Now, as of my knowledge cutoff in 2023, it very clearly this language model, the version was 2024. That's different because the knowledge was collected latest as of 2023. So this is the point where the data was freezed. It's always static, right? It's not dynamic. There are other ways to make it dynamic. That's a different thing. That's an agentic system. That's a different conversation. I'm not getting to that right now, but all machine learning, deep learning, generative models, inherently we are working with static data. Up to a certain point in time, the data was collected, let's say in some kind of a CSV file. I'm just giving an analogy right now. So you have some kind of a CSV file where that huge amount of internet scale text data was collected. And on that, you trained the model. You took a lot of time to train the model. So you can see OpenAI freeze the data in 2023, October, and they took almost a year to release. That means in the span of that 1 year, they were doing a lot of things. They were trying to train the model, fine tune the model. They did a lot of things in the span of that 1 year on the same knowledge data that they collected. And then finally, after 1 year from the data, they release the model. Okay, you can already see the amount of gap. Okay, and then obviously the more recent models like GPT 4.1 and all are trained on more recent data. Okay, so same for machine learning and deep learning tasks also. You will always be working with some kind of static data. It could be a CSV file, which is the very popular file format to work with. So the data is always static and it's always stale up to that particular point in time till which you have collected the data. And then you have to retrain the model. A very important concept in machine learning is model retraining. So you take some data, use some algorithm, build a model, whatever we have done in all these demonstrations and case studies. And now the next thing that you try to do is you try to retrain the model. Now you try to take some sample data and try to retrain the model. You try to take some sample data and incremental data and try to retrain the model. Make something better. So how you can retrain the the model based on the incremental data. So that's another something that to keep in mind. Okay. I will talk a little bit about Azure as we go along. So we have enough time for that. So we'll come to that conversation. So for now, let's go back to the uh, the algorithm. Before that, I was discussing about this. So data discovery, ingestion. Then you go to data wrangling. This is the part where you pre-process the data, you prepare the data, right? So this is the data wrangling part that you do. So you take the data and you pre-process it. You remove missing values, remove outliers. So it's a bit of basic blueprint that tells you what are the different steps involved and what are the different things you broadly do, right? So this is the part where you look at the skewness, you try to apply power transforms, you try to scale your data, right? You might want to join or merge your data if your data comes from different sources. So all those things we will try to do, right? So yeah, data exploration is the part where you try to create some charts, you try to create some visualizations. So correlations, scatter plots, histograms, all of these things broadly we have seen. right? It is very, very exhaustive. But what I tried to do in this summary is to highlight some of the key things that we try to do. But it's an exhaustive list. If you Google out, there are hundreds of different visualizations that you can create in Python. But these are some of the most important ones that you look forward to. And then we come to model building, model selection. This is the part where you try out different algorithms. You try building different models, all of what we have talked about, right? So prepare, train, test, decide on supervised, decide classification, regression. So build the model, predict, find out the performance, compare the performance of different models, right? Boost the performance of the chosen model. How do we do it? We do it by hyperparameter tuning. So this is all a set of steps, right? So you build a model, evaluate the model using confusion metrics, accuracy, training, testing scores, cross validation, right? And then you try to use hyperparameter tuning to boost the model performance. So once all that is done, now we move the model to production as a pickle file. Now this part we have not seen. This part we have not seen. I will discuss that later. How to productionize a machine learning or deep learning model. We'll see that on the last day once I complete deep learning. So once you're done with the whole thing, you take that that sklearn object, or you take that keras object, which is nothing but a simple Python object. Okay, you have a variable. So right now you have a variable in Python. It's like an object in Python. Now you take that Python object and you serialize that into a pickle file. Okay, because you need to move it, you need to deploy it, right? So for that, you need to first convert it to a pickle file, and then you deploy it. This is the part we will discuss later on. Okay, and finally, the last part is explainable machine learning. This is the last step where you try to uh, explain your machine learning models to your stakeholders, right? So for example, all the business cases that we talked about, lead scoring, and all that we discussed in the course of the last few hours or so, and all of these ultimately you need to present to your stakeholders, right? You need to explain the results of these models to your stakeholders. Okay, your stakeholders need to see what exactly you did. That's the whole idea. Okay, I'm sorry. I will discuss. I will discuss. I will talk about it. I mean, I'll take you through it step by step, how to access, what to access. So right now you only have the Azure access given to you, but what is to be done, what is to be checked, that's a bit of a different conversation. Yeah. So Azure is only a very complementary part of this discussion we are having. So it won't be a huge focus, but I will show you. I'll show you every single aspect of it in a while. Okay. Yeah. Yeah. I'll do that. The one that I sh the one that I showed you was something very deep. Um, Let me see if I can cover this up a little bit towards the end of today. Otherwise, it will be the start of tomorrow, either of the two. Okay, yeah. All right, all right. So this is just to summarize the different types of algorithms that we have here, as I was discussing. So this is just to give you a very, very broad summary in terms of what the different types of algorithms are. Again, each of them are very, very theoretical topics. Okay, each of these algorithms are very theoretical, but from an application perspective, just remember what these are. Okay, I want to also let you know that there is no one single rule book that tells you that which algorithm will work in what scenario. Okay, so you will have to try out in the real world scenario. If you want to implement these things, you will have to try out different algorithms, and you will have to compare the performance and see which one gives the best results. Okay, but there is no one size fits all. There is no one template that you have which will tell you that, hey, this is my data set, and for this kind of data, I will apply this algorithm. This is a common question that generally people tend to ask, but I want to clarify that you will still have to try out. It is a highly experimental domain. So if you so it's something we have been doing through our exercises also yesterday, today, some very basic academic exercises that we did. I think this is the learning that most of you would have got by now, that you try out different techniques, you try out different methods, you try out different algorithms and see which one is giving you the highest cross validation scores. Okay. On regression on the left hand side, we started off with linear. You can be polynomials also. Okay. So on the right hand side, we have on classification, we have something called logistic, and we have something called knight base. Knight base is based on the Bayes rule of probability. It is a probabilistic model. Because in classification, inherently, what are we doing? We are trying to calculate uh, what is the probability of something based on something, isn't it? If you go back to all the classification exercises we did, let's start off with yesterday, diabetes. What are we trying to do in the diabetes exercise? We are trying to predict what is the probability of diabetes given the different features of the person. So given their blood pressure, given their body mass index, given their glucose levels, what is the probability that the person will suffer from diabetes? So inherently, if you go back to the principles of probability, it's a conditional probability problem, right? So you're trying to predict the probability of something given something. And that is exactly what Naive-Bayes will do. Okay, so logistic will do it a little differently. Mathematically, it does it a little differently. There's an equation that we get. So that's the theory part of it. But Naive-Bayes does it a little differently. So all of these are ultimately doing classification. All these methods are ultimately doing classification, but they're doing classification in different ways, which is absolutely not, you don't need to know the theory at all for this. Okay, and even if you know the theory, it will not help you solve problems. Okay, as I told you, and as I've mentioned it multiple times, there are two very different learning paths. Okay, and something I encourage each one of you to do. So please do not waste your time going through another 6 months course and studying these theories, because solve problems, look at the applications, and based on the limited understanding we are getting here, get into problem solving. Okay, because knowing the theory will not help you solve the problems better. Okay, knowing the methods will, but knowing the theory behind the algorithms will not help you generally. Okay, so decision trees are basically applicable for both regression and classification. So decision trees are something that is useful for regression models also, classification models also. And if you are using the packages, you can use something called a decision tree regressor, and you can use something called a decision tree classifier. Random forest and gradient boosting, these are basically, if you look at these three categories especially, these are basically collections of decision trees. Okay, so at a very high level, these algorithms are effectively collections of decision trees. Okay, so we can take a particular data set and we can build a single decision tree model on the whole data, right? That's one of the ways how we can do it. So we can take a single data set and we can build one single decision tree model on the whole data. That's one of the ways how we can approach. Or what we can do is we can build multiple decision tree models across our data. Okay, and this is the idea I was trying to mention a little bit yesterday, the idea of ensemble. So these are like ensemble techniques, right? Just to clarify. So decision tree is an individual model, but if you look at these approaches, especially random forest, gradient boosting, extreme gradient boosting, extra trees, stacking and voting, these five algorithms are what we refer to as ensemble algorithms, right? And generally, they tend to perform very well. Result wise, these are like the gold standards. And out of all of this gradient boosting is like an absolute gold standard. So if you look at any typical competition or a real world use case where somebody is using machine learning, usually gradient boosting is a default that everybody will use. Okay, if you talk to anybody in your data science team and if you ask them that, hey, what kind of algorithms are you using? Maybe 9 out of 10 times they will tell you that we are using gradient boosting. They will not even bother to talk about logistic or decision tree or any of these other things. So 9 out of 10 times you'll hear the term gradient boosting. Okay, so at a very high level, what is happening? What is this ensemble thing? What is the meaning of this ensemble? Something I was mentioning yesterday also. So ensemble refers to a group, right? Ensemble means a crowd. It's a group. Wisdom of the crowd. So ensemble basically refers to a group. That's the way we can understand the meaning of an ensemble in a way. Right? Okay, so you have a group of models. That's the idea. Okay, you have a group of models that you're taking. So think of a scenario where there is a committee. Okay, imagine there's a committee and the committee has to take a decision whether to do something. Let's say it's a company and the company has to take a decision on funding. Okay, so it's a small startup company and they're trying to get some funding from some external stakeholders, shareholders, and let's say there's a committee that will have to take a call. The committee has to decide whether the funding should be done or the funding shouldn't be done and all that stuff, right? So the committee has to decide. Okay, so a lot of real decision making will happen in committees like this, like a lot of real world decision making will happen in committees. Because if you ask one single person to take a call, Okay, if you ask one single person to take a call, then that decision might be highly biased, right? So it's very much possible that if you ask a single person to take a decision, that decision might be highly biased. Okay, so that person might decide based on their own interest. Okay, so similarly, if you have some data and if you use a single model or a single algorithm to do a prediction, that prediction can be highly biased. We might end up with issues like those skewness and those kinds of imbalances that we were discussing. So there's some mathematics around it, but generally you get the analogy, right? So you will end up getting incorrect results for certain types of data because certain models will not learn certain patterns correctly. So instead of using a single model to do a prediction, what I can do is I can instead use an ensemble model. I can use a group. So just like we have a group of 5 people in the committee. So each person will take a decision. Person one will say this. Person one will vote yes. Person two will vote yes. Person three will vote yes. Person four will vote no. Person five will vote no. Three people yes, two people no. So the model will predict yes. That's the idea. That's the idea of ensemble. And you can think of any real world decision making, like let's say jury. If you look at very important court cases that are fought, so there's a jury. There's not one single individual who decides what to do, but it's usually a jury, a group of people who decide whether the person is guilty or innocent. A jury will decide. A jury will be part of the trial. Okay, so there'll be a jury of 10 people, and 9 of them say the person is guilty. One of them says the person is innocent. So we listen to all of them and we'll take an aggregate decision. That's the whole idea. And generally, it has been proven, and we have got a immense amount of data to generally see that ensemble models generally tend to work better because they are based on the philosophy of wisdom of the crowd. The crowd as a whole always does better. Okay, so each of the individual models in the ensemble are very poor. Let's say we have got, 5 different models: model one, model two, model three, model four, model five. Now, each of these individual models can be very basic. Model one is like a normal, decision tree. Model two is, let's say, logistic. Model three is knife based. You can have different models also. So each of the models are very basic models. So let's say model one says yes. Model two says diabetes yes. Model three says diabetes yes. Diabetes yes. Model five says diabetes no. Okay. So 5 models, you will individually look at their 5 predictions. Given some X, each of these models will predict 5 values independently, and then the majority vote will be taken. So the ensemble as a whole will predict yes. So this is the idea. So for classification, you will do something like a majority vote, or you can take weighted voting. And for regression, we will do something like an average or a weighted average. Because regression, we are trying to predict a numerical value, right? So this is the general concept of an ensemble. And these are all the different types of ensemble algorithms that are there, which they have variance in regression and they have variance in classification. Again, because our focus here is hands-on, our focus of these sessions are completely hands-on. When you're using this in Python, you will use random forest regressor. Similarly, there is random forest classifier, gradient boosting regressor, gradient boosting classifier, extreme gradient boosting regressor, extreme gradient boosting classifier. This is actually called XGBoost. So this is the full form, but the short form is something called XGBoost. XGBoost is also a very, very popular algorithm. Okay, it's a lot faster, it's more parallelized, and you can read about it: XGBoost regressor, XGBoost classifier. So these two are two of the most popular machine learning algorithms out there. Then there are SVMs, extra tree stacking. Okay, there is something called SV, support vector classifiers, support vector regressors, SVR, SVC. You can Google out these things, but this is just to give you a very broad understanding of the different types of algorithms that you will ever come across. Okay, this is by far the most exhaustive list. There's nothing else that you will see, at least in the open source repository, because we are still using sklearn. Well, obviously, if you go to other platforms, if you go to, let's say, the same machine learning concepts are used in other places also. Okay, let's say you've got Spark. If you know Apache Spark, Spark has something called Spark MLlib. So Spark MLlib is the native machine learning library in Apache Spark. Okay, so yeah, so different languages might have their own different frameworks will have their own machine learning algorithms built into it, but the core concepts are still the same. Okay, if you have decision tree here, you will have a decision tree somewhere else. If you have random forest here, you will have an ensemble or random forest somewhere else. The core ideas are the same. Well, you will, if you go to more paid platforms or other platforms, you will see some different variants of algorithms. Okay, like for example, if I go to Azure, Azure has different thing, something else. It doesn't exactly have something called a random forest. Okay, it has some other term, but the idea is still the same. If you go to AWS, AWS has something called AWS SageMaker. Inside SageMaker, they don't have something called, let's say extra trees classifier, but they have something else. They have some other similar algorithms that are again proprietary to AWS SageMaker. Okay, so these are again some of the important concepts to keep in mind. So enough of supervised learning, and now we'll be getting into the beautiful world of unsupervised learning. We'll start to talk about unsupervised learning and talk about the different types of problem domains that we have in unsupervised learning. What exactly is unsupervised learning, right? Uh, Now, if you remember, we had this conversation right on the first day when we were explaining about this beautiful example of fruits, right? So we had different examples of fruits, and we discussed how you can teach a small kid. How can you teach a small kid about different types of fruits? So you have to tell it. You have to show the example of the fruit. You have to show it a picture of an apple and say that, hey, it's an apple. You have to show it a picture of a guava, and you have to show it that, hey, it's called a guava. So this is how we will do supervised learning in the real world. We will show the machine lots and lots of examples of pictures. So in this case, we will show the machine lots and lots of examples of what apples look like. We will show the machine lots and lots of examples of pictures of how guavas look like. And based on that, we will build a model. And these are the XY combinations, right? Now, unsupervised learning is that kind of machine learning where the outputs or labels are not defined. It was a very crude definition that we had on first day, and what I will try to do now is I'll try to add more depth to this definition. We'll try to get a little bit more in detail as to how and what this means. What is the meaning of outputs not defined? So if output is not defined, what does it even mean? What are we trying to do? Okay, so that's the idea, but this is the broad definition. Okay, so you don't have any outputs, you don't have any output y's in unsupervised learning. So how is it possible? How is it possible that we don't have an output? Well, let's look at this. So we'll look at a very basic problem to start with, a clustering use case, a clustering or a customer segmentation use case. So clustering is one of the most important problem domains of unsupervised learning. So unsupervised learning is a broad category. So what are the different ways we can do unsupervised learning? One of it is clustering. What is it? What are we trying to do in clustering? As the name suggests, in clustering, we are trying to form groups and clusters of data. So imagine we have, we are looking at an Amazon or an e-commerce kind of data, and this is the customer level data that Amazon is tracking. As an example, it is tracking the amount of time the customer is spending in the application, because we all have the mobile app of Amazon, we all have the Amazon website. So next time you log into your account and you go to Amazon apps. Next time you log into your account and you go to uh, the website application. When you do that, what happens is Amazon is automatically monitoring the amount of time that you're taking. It is automatically monitoring the amount of time that you're spending on the application or the website. And it is also monitoring, if you make a purchase, it is monitoring against that same customer ID, against that same account, it is monitoring how much of purchases the customer is making from the website. So both the things they are tracking. So they're tracking the amount of time the customer is spending on the website, and they're also tracking the amount of money the customers are spending on the website. So both they are tracking. If you think about it, these are just features. If you think about this entire thing, these are just features. We just have features of the customer. So we are just tracking the amount of time spent and the amount of money spent. This is just inputs. This is just features. There is no output here. There is no labels that we are getting here, right? Think about it. So when you look at this kind of data, we don't really have any labels per se, right? There are no labels, just features. Just features is what we have. That's the way to look at it. What I can do is I can also try to visualize this data in a kind of a scatter plot, you can see. So along the x-axis, I'm tracking the time. Along the y-axis, I'm tracking the amount of money spent or the total value that the customer has contributed to Amazon. And this is how I can go and plot the data. Every single dot that you see on the screen, right? So every single dot that you see on the screen, it corresponds to what? Every dot corresponds to one customer. So each and every dot on the screen corresponds to one customer. And for every customer, we are tracking how much of time the customer has spent and how much of value the customer has spent, how much of time the customer has spent on the site, and how much of value the customer has spent on the site, how much of time the customer has spent, how much of value the customer has spent. And the moment you plot this data, again, you can see there's no outputs here. This is just inputs. This is just things we are observing, features, right? You remember those are some of the terminologies that we use. We call them X or inputs or features. These are just features, right? These are basically nothing but features. These are features of the customer, and they can be more. They can be more. You can track the um, total value of purchases. You can track number of orders, right? How many frequency of orders? When was the last order placed? All of that you can. For a customer, you can track multiple things. But whatever you're tracking, ultimately, you are only looking at the features of the customer. Okay, and then you can go and group the data into different clusters. So now you can group the data into different groups or clusters or similar groups and clusters. So you can see that, okay, these are customers who are very similar because these kinds of customers have spent less time and less money. The engagement is very low. For some reason, they are not, opening the application or opening the website. For some reason, they are not buying. Maybe they are not comfortable with the online experience, whatever. On the other extreme, you've got customers who are spending a lot of time and a lot of money. So this is like very, very high engagement customers. So this is like a win-win for the company. And on the another category could be very interesting discovery. These are customers who are spending a lot of time. So they are spending a lot of time going through my products and all that I have got. But for some reason, they are not converting. This is a big loss for the business, right? Because at the moment you're spending time, you're actually using a lot of server resources because to render these websites takes a lot of hardware, lot of computing power is needed to keep these sites running so that they're accessible to users. Now, if these users are accessing the site, if they're using all the compute and all that, but no, they eventually don't end up buying anything, and that's a loss for the business. Okay, so now a big part of maybe what they might want to do going forward is uh, how do we go and make the experience better for these customers, and how can we make them buy something. So the first part of the exercise is where we study our existing groups of customers. We identify what are the different groups and clusters of customers, and the next part of the use case would be to look at each and every one of those groups. Now you look at each and every one of those different groups of customers, and you try to figure out how can we target those groups, what can we do, and how can you effectively target those different groups and clusters of customers. Okay, so if you look at customers in group 3, so you identify, okay, these are customers who are very similar. These are customers who are spending a lot of time, very less money. So once you identify all the similar customers in that group, now you try to figure out what I can do, how I can target these customers more effectively, what I can do to maybe make them shop more. And nowadays, if you see a lot of these e-commerce platforms that we see, a lot of these grocery platforms that we see, if you're using Big Basket, Swiggy, Instamart and all, see, when you add items to the cart, they are constantly pushing you to purchase, right? So that is also very interesting. This is a cart prediction model, like a purchase prediction model. So the companies are looking at your cart value. They're constantly looking at all the items that you have in the cart, and they are trying to predict what is the probability that you will actually purchase. And if your purchase probability is low, they will dynamically give you some discounts and make you purchase, which is why, let's say you add some items in the cart and then you log off and you come back after 1 month. and the company will remind you that, hey, you have some items that are in the cart. So please do a purchase now, and I will give you 30% off. Okay, so they are using machine learning to identify the the probability of purchase. And if you're a customer who is likely not to purchase because you see the price is very high and whatever, so if you're likely to come out of the site, then they will give you a dynamic discount and make you purchase. Okay, so a lot of machine learning and behavioral analysis is used to you know entice customers into buying more and more and more. Okay, so we are also like becoming a more and more consumerist society. Anyways, so this is the big part of what we are trying to do conceptually when we are doing clustering. There is no outputs, you only have the input features, and you're trying to find groups or clusters of data. Okay, you look at the existing data and you try to find out the different groups or clusters of data. That's the core idea of what we are trying to do in clustering. And in a way, I would say it is advanced EDA. In a way, it is advanced EDA. Like, when we talk about EDA, what is EDA? EDA stands for exploratory data analysis. So EDA refers to exploratory data analysis. So a big part of what we are doing here is, I would say, kind of like advanced EDA. Okay, you're trying to do EDA in a more advanced manner. You're trying to explore your data. You're trying to find out the different groups or clusters, and you're just trying to do EDA in a bit of an advanced manner. Some other applications of this clustering could be anomaly detection in credit cards. Okay, we did a credit card case study already. Uh, a very good use case how we can translate this problem to a unsupervised learning problem, which is what actually happens. A key terminology that we use here is anomaly detection. Now, you have to understand when we talk about credit card transactions particularly, it is very hard and almost impossible to label the data in advance, right? So having the label data is very difficult and almost impossible. I'm saying almost because retrospectively you can still label. Let's say customer raises a complaint that, hey, some fraud happened. Then the bank will retrospectively label the data. That can happen. But initially, that data is not labeled, right? You're dealing fundamentally with unlabeled data. That's the way to look at it. So you're dealing fundamentally with unlabeled data. You've got some data which is not labeled. You've just got the transaction details that are present right now, X1, X2, X3, X4, X5, up to X7, X8. You've got the different features of the transaction, and based on that, you're trying to identify anomalies. So again, you can see in this kind of data, there's no labels, there's no why. Okay, we only have the features of the transaction. You take the credit card out and you make a transaction. You do a swipe. You go to a merchant and you swipe something. When you do that, you're basically getting some data. Now, what kind of data do you have there? You've got date, you've got merchant name, you've got transaction value, okay, time of the transaction, what is the merchant category, all that. What is the country? Okay. So based on that, again, you are trying to find groups and clusters of data. It's again a kind of a clustering problem if you think about it. There are no outputs because you will never know. You will never know a fraud happens unless somebody reports it or unless somebody labels the data. And getting that data usually is very hard. Okay, again, there are different ways of doing it. There are semi-supervised learning techniques we use, but again, just to keep things simple, think of anomaly detection as a clustering-based approach. You only have the unlabeled data, you have the transaction level data, and you're trying to find groups or clusters of similar transactions. And what you're trying to identify here are outliers. Okay, if you see lots of transactions are like this, like this, like this, and there is one transaction which is like this all the way here, so which is somehow very different. So most likely it's a fraud. Okay, so that's the filter. So this is one of the ways of doing unsupervised learning, clustering. Okay, another related area is going to be recommender systems, right? This is the other thing I pointed out. So recommender systems is like typically your YouTube, and you open up YouTube and YouTube recommends videos to you. You go to Spotify, open up Amazon Music, which recommends music to you. Okay, or you go to Amazon e-commerce, you see that entire homepage and how it recommends different products to you, or Netflix, how it recommends videos to you, or maybe Facebook and LinkedIn, how it recommends jobs to you, or maybe how it recommends social connections to you, maybe likely friends or people you may know. If you look at all these kinds of features, they are totally based on recommendation systems. The recommendation system also is a very good example of unsupervised learning. Now, I'll take a simple example to highlight the concept. So if you see, what I try to highlight here is a use case like Netflix. Okay, so there are two things, right? One is there are customers. So one is there are subscribers. If you subscribe to Netflix, you're a customer of Netflix. And second is there are items. Items are basically the like the movies or the videos or the documentaries that Netflix has in its catalog. Okay. All that we are trying to do, all that a recommendation engine like Netflix is trying to do is it is trying to find out the correlation between customers and items. That's it. If you think about it, there are no outputs here. It is just collecting data real time. It is just collecting data as and when different customers are signing in, different customers are watching different movies or videos or items. Okay. A more technical term to use here would be customers are interacting with items. You're a customer, you click on a link, that means you're interacting with an item. Okay. So you're studying these interactions. So Netflix is collecting this huge amount of data. It knows everything about the customer. It knows where is the customer accessing the site from, what is the age of the customer, what kind of videos the customer has watched. These are all customer attributes. And you can basically build a profile of the customer. If you know the customer's history, what kind of things they watch and all that, you can build a basic profile about the customer. And then you are also studying what kind of things the customer is watching, the item attributes. Item attributes means, let's say I'm clicking on a movie Transformers. So now for the Transformers movie, what are the different attributes of the Transformer movie? Okay, it's an action movie, it's a science fiction movie. The director is this, the runtime is this, the box office revenue is this. It is very similar to that data set one of the folks showed us in the morning session. You will have the genre of the movie. What is the rating of the movie? How much people have rated in IMDb? Rotten Tomatoes, what is the rating? So those are item attributes. So this is all we have, right? If you think of a recommender system like Netflix, which is one of the most powerful and one of the pioneers in the field, right? A lot of recommendation system, Netflix has been one of the pioneers in this field, right? It's very good in what it recommends. So it is completely unsupervised. It's not labeled. The data is not labeled. It is not that somebody is giving an output value explicitly. No. You're simply studying features of the customer. You're simply studying features of the items that you're watching, and you're trying to draw correlations. You're trying to draw some mapping. And then on the basis of that, you're recommending that, hey, you know what? Customers like this typically watch items like this. Customers like this typically watch items like this. You're drawing correlations. And then next time you have a new customer, it's saying, hey, I think you might like this. See what I'm getting at? And the same idea you can extend to other platforms. Let's say if you go to Spotify, music, doesn't matter, right? So, users and items can be different in different places. If you go to Spotify, customers are the same, customer attributes, and item will be the song, music, attributes of the music. When it was released, runtime of the music, how many minutes, 3 minutes, 4 minute song, genre of the music, right? Artist name, all that. Some kind of audio features, maybe. If you can look at some kind of audio features like is it how many beats per minute? Okay, what is the bass? What is the frequency, wavelength? So different types of maybe if you're doing some kind of spectral analysis, you can get some numerical features of the audio. Okay, so those are kind of things you can do. That is all part of the data basically. Okay, that's the idea. So I hope everybody has a good, solid understanding with what is unsupervised learning. It's not so the ideas are a little different. We will be solving the problems a little differently. It's a lot easier. Okay, and and here we will not be following the same approach like the train test plate and building the model, evaluating the model, because there is nothing to evaluate, right? There are other ways to evaluate, which we'll see. Okay, which we'll see. What are the different ways to evaluate? We'll see. But we do not technically have a testing data here. Okay, so when you think of an unsupervised learning problem, we technically do not have a testing data. We don't have a evaluation data. We don't have a ground truth. We don't have something called Y to evaluate against. So supervised learning, we could do that very easily. We can say, hey, the model predicted this Y. Is it matching the actual Y? But here, there is nothing like it. There's no labels, right? So there are different methods we use to evaluate, which we'll see. And this is going to be a very broad discussion. Okay, so just to give you an idea in terms of how it's done. But the initial part is very important. Like And that's what we really encourage you to do at, in this part of the, like in this phase of the session, where we want you to look at a problem and we want you to identify what type of problem it is. That's one of the first things you should do, right? So let's say if you're looking at networking data, if you're looking at your network parameters data, and if you're just studying the data, it's a very good use case of clustering actually, because you don't have any labels, right? You're just trying to look at your data and identify and cluster that into different groups. You're trying to find out different groups, like, okay, these are groups like this, these are groups like this. And then retrospectively, you can go back and study those groups. What is group one? What is group two? What is group three? Okay, we'll build some more clarity as we see some core techniques. So I will start my conversation and I will discuss a very basic algorithm called k-means clustering algorithm. So we'll start with something called k-means clustering, which is a very, very basic way of doing clustering. And with that, we will be able to get some very good concept and very good understanding of exactly what is happening inside clustering. All right, so now we'll try to understand what exactly is the k-means clustering algorithm. So let us see the diagram and try to understand it step by step, what exactly is going on. So first we look at the top part of the picture, and the top part of the picture, we have again the typical unlabeled data that we have been discussing so far, because we don't have labeled data for unsupervised learning or clustering. So we have completely unlabeled data. And you can think of each of these dots as customers, right? So every dot is, let's say, one customer. So each and every dot is, let's say, one customer. So one dot corresponds to one customer. So that's the information that you have. And all that we are trying to do is we are trying to find what are the different groups and clusters of data. So it's a two-part problem that we are trying to solve. So we are doing two things. One, we are trying to figure out how many groups and clusters of data you have. That's A. And B, you are trying to find out what are the centroids of the clusters B. Okay, so there are two things we are trying to do. There are two things we are trying to do, and there are two problems that we are trying to solve. So first, we are trying to find how many groups and clusters of data we have. That's A. Okay, so how many different groups and clusters of data we have? So we can very clearly see that there are three different groups and clusters of data. And B, we are trying to find out the centroids of the cluster. So that is exactly what the algorithm will help us achieve. So what are the steps of k-means? So k-means I'm trying to take you through, because k-means is a very easy algorithm, although the focus here is not too much on theory and algorithms, but this algorithm I'm taking you through because it's very simple. This is hardly 5 minutes it will take. So first, what we do is we randomly initialize k cluster centroids. So step one of k-means, what we do is we try to randomly initialize the k cluster centroids. Okay, because remember, we are trying to ultimately find out the positions of the centroids. We are ultimately trying to find out what the centroids are. So the very first step that we do is we try to find out what those k cluster centroids are. Okay, so k is a variable. So in this case, the value of k will be equal to 3. Okay, because I told you initially we do not know what the centroids are. So first you define k cluster centroids. You initialize k cluster centroids to start with. Next, what we do is we assign every single point to its nearest cluster centroid. You assign every single data point to its nearest centroid. That is the next thing that you do. And then you reposition the cluster centroids. Okay, then we reposition the cluster centroids. And we keep repeating steps 2 and 3 until no further assignment happens. Okay, so this is the algorithm of k-means. I know it's a lot to take in. So what I'll do is I'll try to give some animations and help understand this concept better. But just give it a glance again, all of you. So first step, randomly initialize k cluster centroids. Initially, you initialize the centroids here, here, wherever. You randomly initialize the k centroids. Step 2, we assign every data point to its nearest centroid. So we assign every single data point to its nearest centroid. And step 3, we reposition the cluster centroids. And we keep doing this over many, many iterations. Many iterations, we keep repeating the steps until no further assignment happens or the cluster centers stop moving. So that is effectively what we are trying to do. So just to help you relate to this a little better, I will parallelly open up this visualization for you. Let me quickly try to take you through this, pictorial approach. So I will take a simple example of a Gaussian mixture. I think it's very obvious here how many centroids and how many clusters are there, but let me anyways take you through it. So there are three clusters that are visible, and I want to find out the exact position of the centroids. So how do we do it? So first step is, again, we randomly initialize three cluster centroids. So let's say I start with three random centroids, somewhere here, somewhere, and I'll try to keep it like a little confusing, keep it midway, somewhere here, and I will try to keep the next centroid somewhere here. So you can see the initial centroids are completely random. They are not perfect. Centroids are basically averages. Okay, so what is a centroid? Centroid is an average. Centroid is the middle value. So ideally, the centroids are supposed to be here, 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 and here. But as I said, this is not something that you will do manually. You will not do clustering manually. You want an algorithm to find out the groups and clusters for you. Okay, so you do the initial centroid placement, and then the algorithm will iterate and find out the exact position. So, okay, so first step is this. Second step, what we will do is we will try to find out uh, the distance of the data points from the respective centroids. So we will assign every data point to its nearest centroid. So if you look at all these data points will be assigned to red. The moment I hit go, if I click go, what will happen? All these will be assigned to red. All these will be assigned to blue. These are also blue because they are closest to blue. And all this will be assigned to green. So we are in step number 2 right now. Then we will do step number 3. We will reposition the cluster centroids. So reposition means what? Reposition means we will recalculate the centroids. So centroid is average. So initially the centroids were here, right? Green centroid was here. Now all these points are part of the green centroid, right? All this is green. So you will recalculate your green centroid, and the green centroid will move somewhere here. Okay, so when you update your centroid, the green will be here, the blue will be kind of somewhere here, and the red will be kind of somewhere in midway. So when I update the centroid, see what happens. The green moves here, the blue moves here, and the red moves here. We have completed step 3. Now we are back to step 2 again. The position of my centroids have changed. Now the green centroid is here, the red is here, the blue is here. Now with respect to that, you try to again assign every data point to its nearest centroid. Now with respect to this new centroid placement, which we just now updated in the previous step, now you try to again see, okay, which points are closest to green, which points are closest to blue, and which points are closest to red. So reassign points. Look at the magic. So now all these are part of green, all these are part of blue, all these are part of red. Now click on update centroids. That's it. So step 3 completed. Again, if I do step 2, nothing will change. So now you keep doing step 2, step 3, step 2, step 3. Nothing will change. Okay, so this is how the k-means algorithm works out. So we can do one more example, slightly more difficult one. Let's take a packed circle. So I'll define my 7 centroids: 1, 2, 3, 4, 5, 6, 7. Okay, so we initialize with the 7 centroids. So first step, you assign every single data point to its nearest centroid. Step 2, we will reposition the centroids. Step 3, we will assign. Step 2, assign, reposition. So you keep repeating step 2, step 3. See how the centroids are changing. So keep repeating step 2, 3, 2, 3 until there is no further change that happens. So the end result of clustering, that is what is more important. Now, this was all the theory that I took you through. But the end result of clustering would be, I give you any data, and the clustering algorithm or the clustering model will give me the centroids of my data. Okay, it will clearly tell me that, okay, there are these many number of groups I can see, and these are the middle point of your groups. The middle point of the groups will somehow tell me the average behavior of that group, isn't it? I mean, if you relate it to the beautiful customer segmentation use case that we discussed, so if I can tell you, the centroid of the group, if I can tell you that there is a group and the centroid, the middle value is this, inherently it means what is the average behavior of the group. It tells you on an average how the group behaves. Okay, so if you relate it back to the initial conversation we were having, customer spending time, customer spending money. So when you have a centroid, the centroid will kind of tell you the average time spent, and it will tell you the average money spent. What is the average time the customer spent, and what is the average money the customer spent on the site? Okay, so this is going to somehow define the group for you. Okay, so we've got one more very interesting analogy that I wanted to take for everyone. This is another very nice animation that I wanted to play for all of you. So you can see. Let me kind of play the animation again. I'm not showing the algorithm again because all of you recall it to some extent now. Look at this one. So first step, you can again see that we are going through the centroids. Okay, everyone can see this now. You can see first step we are initialize. Second step, assign every single data point to its nearest centroid, and third step, reposition. See, this is assign, then reposition. Again assign, then reposition. So it goes through the step 2 and step 3 are repeated multiple times. We repeat step 2, step 3, step 2, step 3 multiple times until we are able to find the exact values of the centroids. Okay, so this is again the theoretical part of the algorithm that we discussed all this while, just to tell you how the algorithm is working per se, right? I can play this once again for you. This was a little bit fast to take in. So let's look at another analogy. So here it goes. And once again, you can see step 1, we initialize the centroids, the 4 centroids. Step 2 is assign. So this is step 2 happening. We are assigning every single data point to its nearest centroid. And then step 3, reposition. The centroids are repositioned. See, the greens are repositioned. Again, step 2, assign. Step 3, reposition. Step 2, assign. Step 3, reposition. So we keep repeating steps 2 and 3, steps 2 and 3 like this until no further, like until we get the exact positions of the centroids. That's the way how the k-means algorithm will play out. So now we'll go to a real use case. We'll go to a small case study in terms of how to implement k-means, because that's again the major focus for us. We're trying to see implementations, how it is implemented. So let us go and check how the k-means clustering algorithm is implemented. And before that, there's one more small related concept I would like to discuss, which is how to decide the number of clusters. Okay, because if you look at the last case study, the last example that we did, I initialized the number of clusters to be 3. So I straight away said n clusters equal to 3. So you find out the 3 clusters for me. But it is also very important because clustering is an unsupervised learning problem. There has to be some way for us to know how many groups we want to form, right? And that is exactly what we will briefly see, how we can use different methods to find out how many groups or clusters to even form. Because the k-means algorithm, it needs the argument. You have to tell it in advance how many clusters you are looking to create. So how to know how many clusters we should go for? Should I go for 3 clusters, 4 clusters, 5 clusters? How do we do that? Okay, so this is just one of the approaches that we can use. There are many other approaches that are there. So what we are doing here conceptually is we are calculating something called inertia. So we are using the inertia metric to calculate the error that is inherently present in the cluster. So we are measuring the error in the cluster using something called inertia. Okay, I repeat again, we are measuring the error in the cluster using something called inertia. And what is inertia? Inertia stands for SSE. SSE is nothing but sum of square errors. So first we calculate the error, then we square the error, and then we calculate the sum of the square errors. This is the 3-part process we are following. So first we calculate the error. So we are trying to calculate some kind of an error. Error in this case is nothing but distance, right? So if you have a clustering model, how do we inherently think of the error in the model? The error is nothing but the distance, basically. How far is the data point from the centroid? That is how we define the error. Okay, so when you do clustering, let's say this is the distribution of data points I have right now, and you find out the centroid. Let's say I did k equal to 4 as an example, right? This is just to explain to you how clustering is happening. Let's say you end up doing k equal to 4. So when you do k equal to 4, when you do clusters equal to 4, what is going on behind the scenes? So when you do clusters equal to 4, when you do k equal to 4, behind the scenes, you are able to find out the centroids, right? Now that you did the clustering, you want to find out what is the you want to now find out what is the inertia of the model. What is the overall inertia of the clustering model? That is what you want to find out. So first you calculate the error, then you square the error, and then you find out the sum of the square errors. So error is nothing but the distance of the point from the centroids. That is how we calculate the error. So we take each and every data point and we find out the distance from the centroids. So we find out how far are these points from the centroids. That is the error. Then we square the errors, and then we find out the sum of the square errors, SSE. Mathematically, if I have to formulate the mathematical formula, it's quite straightforward. You can see that each of these distances of the points from the centroids, these are the distances, like D1, D1, D2, D3, D4, D5, D6, D7. So these are the distances. So first we take the distances D1, square it up, then sum it up. D1 square plus D2 square plus D3 square plus Dn square. So it's actually summation Di square. That is how we define the inertia. Why are we talking about it, right? Why are we talking about inertia? Let's see that. So now what we can do is we can actually plot a graph. We can plot a graph here and say that, hey, whenever the number of clusters is 1, see here we have done 4 clusters, right? Because 4 clusters is kind of optimum. It's very obvious, right? I mean, if you look at this diagram visually, everybody can make out that 4 clusters is kind of optimum here. It is optimum here. So that's what we are doing here. We're trying to create 4 clusters. But what if I create 1 cluster? What will happen if I try to create a single cluster out of the whole data? What will happen if I try to create one single cluster? So if I try to have a single cluster for all these data points, the inertia will turn out to be very high. The inertia value that you end up getting will turn out to be very high. You know why? You know why the inertia will turn out to be very high? Because the distance of the individual data points, like, if I just annotate it and show you, okay, imagine I have a single cluster. So all these points are part of a same cluster. If I do that, then all these data points will be very, very far away from that centroid, right? If I have a single centroid now, so the inertia will be very high. So for cluster 1, inertia will be very high. That is one extreme. The other extreme would be if I have too many clusters, or in other words, if I have too many centroids. Let's say in my diagram right now, I have 100 data points, right? I have 100 individual data points. Every point is a customer. So if I try to identify 100 centroids, if I try to identify 100 centroids, what will happen? The inertia will become 0, friends. Because every data point is a centroid now. And it's like you have got 100 points and you've got 100 centroids. So what is the distance between every point and its centroid? It's 0, right? Because the point itself is a centroid. That is the other extreme. So inertia equal to clusters equal to 1, inertia will typically start very high. And clusters equal to 100, like as many as data points we have. So inertia will tend to 0. We are trying to find out something in between. So as the number of clusters increases, you start with clusters 1, inertia is very high. And as you go from clusters 1 to clusters equal to 2, clusters equal to 3, clusters equal to 4, as you increase the number of clusters, right? So as you increase the number of clusters from 1 to 2 to 3 to 4 to 5, as the number of clusters increases, what will happen? The inertia will continue to decrease. So you can see very clearly we go from 1 cluster to 2 cluster, inertia has dropped a lot. You go from 2 to 3 clusters, inertia has dropped a lot. 3 to 4 clusters, inertia has dropped a lot. Now this is kind of the optimum part, right? 4 clusters kind of seems like optimum. So from 1 to 4, you're seeing a very big drop in inertia because the quality of the model really improved until 4. Now 4 to 5 onwards, something very interesting will happen. The inertia will continue dropping. Definitely, see, mathematically, the inertia will continue dropping because the distance will reduce, right? But we seem to have achieved some kind of an elbow here. This is the bend. And this is what we call the elbow method. This is the elbow method that we are calling. Why is it called elbow method? Because we are trying to find what is the point where we achieve that bend. So from one cluster to four clusters, it has dropped a lot. Four to five, five to six, six to seven is kind of stagnant. It won't be exactly stagnant, it will still reduce, but the rate of reduction is low. So that is that bend that you are trying to find. And this is the way we can, this is one of the most rudimentary ways we can use to determine the optimum number of clusters that we have in clustering. So given any segment, clustering problem, you can straight away do an elbow method because you don't know, right? Say real world data, we cannot visualize. Here we can draw a scatter plot. That's why it's so easy. You can look at this and say, hey, I can see there are four clusters, but hey, what if I give you 10 dimensions? This is a two-dimensional data. It's a 2D data. That's why you can see a scatter plot and you can visually see. But in reality, you will not have a 2D data, right? What if I give you, like the diabetes data from yesterday, and I ask you, please tell me how many groups or clusters of patients we have? How will you do that? How will you study all the 8 different features and tell me how many groups are there? So you need an algorithm. You cannot do it, by hand. You cannot do it visually because you cannot visualize. How do you visualize 8 dimensions? You cannot, right? So so that is exactly where these kinds of approaches are very useful. So you take the whole data, you plug it into an elbow method. You try to find out, okay, clusters one, what is the inertia? Clusters two, what is the inertia? You try to find out that bend, that elbow. And that is what tells you the optimum number of clusters. And once you have the optimum number of clusters, then you can use the k-means algorithm. You can say k-means, and you can find out the exact value of the centroids. And that is exactly the process that we will use now. So we'll go to our very first hands-on example where we will use this exact same process. Okay, so we'll do a small hands-on exercise, and based on that, I will give you a hands-on exercise. And over the course of the next half an hour to 40 minutes, we should have a very strong understanding of how to do clustering. Because I see clustering is going to be a big part of the work that you do. Okay, you're also looking at a lot of machine data, a lot of log data, like a lot of network parameters data. So this is actually a very good use case for a lot of you, right? Because you might want to look at your network parameters data and find groups, find clusters, because there are no labels, right? You're just looking at data that is getting accumulated every timestamp, every millisecond, every second level data you're getting. So it's going to be a very good use case where you want to find groups, find clusters, find anomalies. Okay, so this is something that you can relate to. So this is my data set. The example number one that we are taking up, we are looking at a very simple data set. We are taking a two-dimensional data, you can see. When I do data.head, I am able to see V1, V2. V1, V2 are the two features we have right now. And we can also see the values of the features. Now, V1, V2 are completely hypothetical features we have taken. They could mean anything. You can put you can put a face to the names of the features. You can say V1 is, let's say, time. V2 is, let's say, money. You can think of it in the Amazon context. So V1 tells you how much time the customer is spending on the website, and V2 is telling you how much money the customer is spending on the website. So both of these parameters you're tracking. And now what we will do? Now what we will do here is we will go and on the basis of this data, we will go and try to find out a couple of things. We'll try to figure out how many groups and clusters we have, and second, we'll try to figure out what are the centroids of the clusters. Okay, so let's do it step by step. So first, we will use the elbow method. See, I'm not taking you through the code because this is just Python. I think people are fairly comfortable with coding here, but straightforward. What we have done is we have actually used a range function 1 to 20, and we are iterating through this in a for each loop, and we are basically building different k-means models, and we are basically computing the inertia underscore. So it is a straightforward method that libraries that we are using, and at the end of it all, we will get this. We will see, okay, n clusters 1. When we have one cluster, in error is this much. E6 means 10 power 6. When clusters is 2, see the error has dropped 2.3. When clusters is 3, 6.11. And this is how we can visualize it. See this beautiful elbow that is getting formed. Can you see, all of you? You can see that when the clusters is equal to 1, the inertia is very high. When the clusters goes from 1 to 2, the inertia has dropped. And when the clusters goes from 2 to 3, inertia has dropped further. So it clearly tells you that as the number of clusters have increased from 1 to 2 to 3, as we have increased the number of clusters, as we have increased the number of clusters, what has happened is the inertia has continued to drop. It has gone from a very high value to a very low value when we have 3 clusters. Now 3 clusters to 4 to 5 to 6 to 7 to 8, it is kind of stagnant. It is still reducing, as I told you, it will still reduce, but the rate of reduction is not as high as what we had here. So this is the elbow. So very clearly for this question, what is the optimal number of clusters? What is the optimum number of clusters? The optimum number of clusters we have is equal to 3. So first step, you find out what is the optimum number of clusters. And once you have the optimum number of clusters, then you go and use the k-means algorithm. We have a straightforward library that we can use. This is k-means n clusters equal to 3. And we do k-means dot fit of x. Remember, in unsupervised learning, clustering, we don't have any output y. So even from a code perspective, when we use the sklearn algorithm, we don't say x comma y. Okay, we will simply say k-means dot fit of x, because you're simply using the features and you're trying to build the clustering model only on the basis of your features. So we will say k-means dot fit of x. So we will build the clustering model, and then based on whatever model we have built, we will do the prediction, and we will find the cluster centers. This is the end result of what we will get. Okay, see, so we have the original data points, and we have created a new column called group. And what is this group? The group is nothing but k-means dot predict. So whatever k-means dot fit I did, I do k-means dot predict to get the labels, and these are the labels that I'm visualizing. So this is the workflow. The original data was this, right? V1, V2. This is the original data. The first step, you figured out how many groups we have. That was the inertia elbow method that we used. So, and then we use k-means to find out the exact positions of my centroids. And based on that, we are able to say that, hey, you know what? Data like this is part of group 1, data like this is part of group 2, and data like this is part of group 3. So now we are able to say what each and every group of data entails. Okay, so that's the thing we are able to make out here overall. And we can visualize it in this way. You can see this is the way how we can think of clustering. And as I told you, like here, I know it looks very easy here because it's just 2D data, but it becomes more challenging when you have multi-dimensional data. In that case, you cannot visualize it in this manner. So if you have to visualize it in that sense, you need to create a pair plot. Okay, so especially for a two-dimensional, multi-dimensional data, if you want to visualize, then you will have to create a pair plot like this to visualize. Okay, you'll have the diagonals. So if there's V1, V2, V3, V4, so look at the diagonals, and then you can visualize the data in this pair plot. Okay, and we'll see some of those use cases as we go along. So this is how we do clustering. There are other algorithms we can also use, but the core idea should be very clear. What is clustering? How do we frame a problem? How do we think through it? How do we do it? Right? Even for this part, like if you see my slides, I've also given you lot of reference content I've shared. Right? I'm not obviously it's not possible to go through every single part of it, but I've shared with you other reference content like something like a silhouette coefficient. Right? This is another way we can use to identify how many ideal number of groups and clusters we have. So elbow method is one way, and we have another approach called silhouette coefficient. Okay, so higher the silhouette scores, the better the quality of the cluster. So there are different ways to do these things, but this is the core idea. The core idea should be very important, because once you have the core idea, then you can study, and then you can use reference content. You can use the generative tools to try different methods, and that's the self-learning that everybody can do. Okay, now based on what we have discussed, we will do an exercise. So here goes the solution file for the shopping spending score exercise that all of you did. So if you remember the data set that we had two features. We have the income of the customer, and we have the spending score of the customer. So for every customer, we have two features. We have the income of the customer, we have the spending score of the customer, and we are trying to find the different groups and clusters of customers. Okay, so this is the clustering exercise that we are trying to do. How did we go about it? First step, we think we go and do the elbow method. So the elbow method is clearly telling us that there are total 5 groups or clusters of data. We can clearly see the bend. We can see the inflection point. That means when clusters is equal to 1, the inertia is very high. When we go from clusters 1 to cluster 2, inertia has dropped. When we go from 2 to 3, inertia drops further. When we go from 3 to 4, inertia drops further. When we go 4 to 5, inertia drops further. So we can clearly see that as we increase the number of clusters, the inertia keeps dropping and dropping and dropping until we reach an inflection point, and that is where we can say that we have the optimum number of clusters. Now, the moment we have clusters equal to 5, from here onwards, you can see that there is no further reduction of inertia. Once you touch the inflection point of 5 clusters, from here onwards, even if you increase the number of clusters, you can see it is not improving. The overall inertia remains roughly the same. So now that we know that clusters is equal to 5, we are saying n clusters 5. So we build those 5 clusters. This is the final data frame that we can create, where we had the original 2 features, which is annual income and spending score. And we have added one additional column called the group. So the group is going to tell us what cluster or what group that particular customer belongs to. So this customer belongs to group 1. This customer belongs to group 4. This customer belongs to group 2. So this is the final part of the clustering that you can go and do. And based on the question that one of you are asking, the final part will be, after you've done the clustering, now you can go and identify what are the different groups and clusters of data. How do we interpret the groups? So you can create a pair plot, and you can create a pair plot or you can create a box plot, and based on that you can interpret the different groups and clusters of data. Okay, the pair plot is clearly telling us that it's able to identify what those clusters mean. An even better way of doing that is actually using a box plot, where you can clearly see and you can compare between the different groups and clusters of data. It's the last part, how you try to interpret the clusters. And you can see that cluster 0, cluster 1 group of customers typically have high income and high spending score. On an average, the customers who are part of group 1 have high income and they have high spending score. Whereas if you look at customers in group 2, customers in group 2 on an average have low income and low spending score. Now, what is very interesting are groups 3 and 4. 1 and 2 are kind of the two extremes, right? One is very high engagement, one is very low engagement. So somehow these customers are not spending. But what is very interesting is groups 3 and groups 4. So if you look at group 3, who are the group 3 customers? Group 3 customers are those customers who have very high income, but who have very low spending score. That is the group 3 customers that we have. And if you look at group 4 customers, group 4 customers have low income and high spending score. That is what we can say about group 4 customers. That is the inference we can make about the different types of clusters. And based on this insight, we can go and further uh, develop business strategies to run our business more efficiently. See, for example, if you come across customers in group 3, now group 3 is a concern, right? Because these are customers who very clearly have on an average a lot of income, but for some reason they are not spending with me. So they have a lot of disposable income with them, but they are not coming to my store and spending money. What could be the reason? Maybe it could be because I'm not stocking enough products which are uh, preferred by this particular group of customers. The other thing is also very interesting, like customers who have low income but high spending score. Now these are like very, very loyal customers, right? These are customers who are very budget conscious customers. They are not the highest earners, but despite having a lesser amount of money, they are still spending a lot of money with me, because most likely this could be that they are coming from a different state and they're mostly freshers. Let's say they're still yet to settle down with families, and they're still buying a lot of items outside. Let's say grocery shopping. You go to usual stop shops and do grocery shopping. This could be some very interesting discoveries you can make. By looking at your data. Again, in all these examples, if you see, we don't have any labels, but we only have the features, we only have the data, the inputs that are available. And based on that, we are creating groups and clusters or segments of customers. And once we identify that, once we see that, hey, we are able to group our data into 5 clusters, now we can try to come up with different promotional campaigns for each of these different groups. So now we can say, hey, you know what? This group 4 is like a very, very loyal group of customers. These customers deserve more from me. If you're the store owner, you will look at this group 4 and say, okay, these customers are, they are like my like my bread and butter. despite having less income, they're still spending in my store. So maybe tomorrow or a year later, if their incomes increase, they will continue to spend more. So we are trying to build that loyalty aspect with these customers more. So maybe for the group four customers, every once in a while, every week, you will give them some nice promotional coupons. Even something as simple as, let's say, you buy 100 rupees worth of grocery, and we will give you a 5 rupee, something like 5 rupee salad for free, something like that. People would love it. They say, okay, this is a good store. Whereas if you look at this group, the group one customers, see, the group one customers are very rich people, right? They are rich people, very high engagement, high income, high spending. So these customers don't want discount, but these customers basically want a good, probably they want a very good experience. So maybe next time you are having all these so-called, new launches, like the way Amazon, Flipkart, they do new launches. Then there's a new smartphone launch, like you have those first day, sales, those exclusive sales that can happen. So maybe this kind of group is looking forward to some kind of an exclusivity. Maybe have a membership tier, start a membership card process, like what Zomato did long back. They started this thing called Zomato Gold, right? There was a Zomato Black membership. Now there are different memberships that have come, but Zomato was one of the pioneers of this, this concept. And they even came up with a credit card. This was back 3-4 years back. There was a RBL bank credit card they used to give out. If you have a Zomato Gold membership, you have this edition. There was a Zomato edition credit card that they came up. Then they eventually stopped it. It's been almost 2.5 years they have stopped the credit card. But these were some very interesting strategies that you can come up with as a business once you are able to see the different groups and clusters of customers. So especially for these kinds of customers, I want to give them some more some more exclusive deals. Some maybe Swiggy. A lot of these co-branded credit cards are there, right? So maybe you can divide it into tiers, right? You can give them a very very low end Swiggy co-branded credit card if you're a low engagement customer, like a something like a group two. But maybe something like a group one, you can give them a really really high end credit card, let's say with some free lounge access and all those kinds of things. Okay, so these are some very practical ways how you will approach these problems going forward. Okay, coming to the next case study, the next case study was very very interesting, and I will take a minute to take you through the case study first, and then I will explain to you. This is a again, the core concept is very similar, but as I say, the next case study, the focus is mostly on the feature engineering aspect. And this is the general context of the case study. So we are looking at a real data set. This is again a real anonymized data set that we are exploring, which has transactional data from 2010 to 2011 for a UK-based registered non-store online retail. And you can see this is my data. Once again, invoice number, stock code, description, quantity. So this is effectively what my data looks like right now. Okay, so let me take you through the solutioning. This is my data set. I've already shared that with you, and I'll take you through the whole solutioning approach, what we have done. And again, the focus will be much on the feature engineering part. How do we take the data? How do we identify the features? So we'll try to focus more on the feature engineering side. Okay, so please, like I've shared all the solution notebooks with you. While you're referring to the notebooks, I would like you to refer to the part one. Okay, the step one part. Okay, yeah. So yes, so you can focus on actually the step two part. Yes. So initially, my data is given to you in a transactional form where every row is like an order. So when you place an order in Amazon, this is exactly how your data is captured at the back end, right? You will have something like an invoice number, a stock code, what you purchased, description of the item that you purchased, how many you purchased, when you purchased, what was the price of the purchase, which customer purchased, like that, so and so forth, right? So you can see we have got invoice numbers. Against the same invoice number, we have multiple items that were purchased, right? So that's the inference we can make out. So you can see against the same invoice number, so it's for 536365, for the same invoice number, we can see there are multiple items that were purchased. And it's possible, right? For the same order ID, you do multiple products. You purchase multiple products against the same order ID. So in the same order, you buy soap, you buy shampoo, you buy oil. So these are the different items that you purchase against the same order ID. This tells you how many you purchased, when you purchased, at what price you purchased, and so on and so forth, right? That's the inference you're getting. Now, the first part of the analysis is you have to understand. That's why I always say that understanding the problem, framing the problem is very important. which is the whole idea of giving you some time to think through the data set. So don't just jump into a solution, because see, if you try to apply the k-means clustering directly on this data set, it will not work. Because what is the granularity of your data? What is the level of detail of your data? The level of detail of your data is actually order level detail, right? Actually, to be more technically correct, it is invoice and stock level detail. The composite primary key of your data set here is invoice number, comma, stock code, isn't it? If you see every unique, what what is the unique ID of this, of each and every record? It is invoice number, comma, stock code. You're looking at order level data right now. So even if you apply the k-means algorithm on this particular data set, you will not end up doing customer segmentation. You will simply end up doing what? Even if you apply this in the data set, you will simply end up doing order segmentation. You will not end up doing customer segmentation. You will simply end up doing segmentation of orders. These are orders like this, these are orders like this, these are orders like this. So in order to do customer segmentation, what do you need? What do you really need in order to do customer segmentation? You need to group this data into customer level of detail. There's a whole lot of feature engineering we are talking about. So we take the original data, we try to do group by, we group by customer ID, and we try to find out three key metrics, three key things we try to find out. Okay, this is an example, but you can do much more. Feature engineering is a very broad universe, and you need domain knowledge to do this. It's very subjective. It depends on your field of work. So here what we have done is, from the original data, we have done group by customer ID, and we try to find out how many orders you placed. This is the most basic one, right? Group by count star. So group by customer ID, do a count star. So for every customer, we are tracking how many orders they placed. We are finding out something called monetary value. There's something called monetary, which tells me the total value of orders that you placed. So for each and every customer, group by customer ID, we are basically doing a sum of amount. What is the total amount that you place, which is in itself is unit price into quantity. Remember, these are the original features we had. It is like we are doing group by customer ID, sum of unit price into quantity. So in a way, for every customer, we are looking at how many orders you placed, total value of orders you placed, historically, ever since you opened the account, how many overall value of orders that you placed. And finally, we are tracking how many days back you last placed the order. This is actually very interesting. This is called recency. A lot of companies, they measure recency. Recency is used as a very useful attribute to understand the active status of the customer. See, for example, I'll tell you something. I last ordered in Amazon long back, so my recency is very high. Let's say I last placed an order 1 year back. So Amazon will look at the current date time. If you look at my last order date, and it will find out the difference in days, and that's the recency value. So for somebody like an Amazon, the recency value is nothing but the current date time minus the last order date. So 365 is the recency value. So for example, this customer, the recency value is 325. That means this customer is currently not active in the platform. Another way to look at it and explore this would be, this customer is presently not active in the platform. So now your objective would be, how can you make these customers, how can you make these customers more active in your platform? What can you do? Because right now, very clearly, as you can see, this customer is not active in the background, in the platform. So very clearly, this customer is not active. So now you have to figure out what you can do to make this customer active. What are the different things we can do to make? So, which is why if a customer's recency value is high, you will often see that the brand will want to offer more discounts to these group of customers. If you have not used Amazon for a long time, if you do not use Swiggy for a long time, okay, let's say Swiggy has Instamart. So you try not using Instamart for 1 month. Swiggy Instamart will give you a free 100 rupee coupon. Why? Because they are sensing that your recency value is very high. You last ordered more than 1 month back. So they are trying to get you back to the platform. They are sensing that you have become inactive. You're probably churned. Churn means you leave Swiggy and you go to some other brand for your groceries. So if they predict that, if they predict that because your recency is high, you're not ordering from Swiggy, so they'll try to get you back. They'll try to give you a 50 rupee voucher or something. So then they will force you to shop. And it's a behavioral thing. Like you shop once and you feel happy, you shop again, and it's a very behavioral thing. But it's quite incredible how these things are actually used. Segmentation, customer segmentation and clustering is at the core of how we see all these promotions, discounts, and how all the grocery, hyper local delivery startups and the e-commerce companies are operating. Even to the point of telecom companies, I would say, because everything, but these are some examples we see on a day-to-day basis. Telecom maybe less so, because honestly, telecom is mass market. There's like I I mean, uh, but yeah, I mean, there's a lot of scope for what you can potentially do. Right? So maybe something like a Reliance Jio or a Vodafone can look at or Airtel can look at your day-to-day usage data. They can try to understand how you're using the connection, and they can try to recommend recharge packs and plans according to how you use. So if Jio sees that you have not topped up for a long time, they might give you a 50 rupee coupon to sweeten the deal, because they think you might have left Jio and went to some other platform. Churn, customer churn is another very important problem that companies are solving. Okay. Anyway, so this is the first part of the analysis, because I think this is the most important part, and this is the part I really wanted everybody to kind of figure out. So if you were able to, then it's great. It's good that you were thinking, but otherwise, this was quite a important part of the problem, because once you have this, there is nothing to talk about. Now it is back to the same template that we discussed. So now you have each and every customer. You have the features of the customer. For every customer, you know how many orders they placed, the total value of orders they placed, and how many days back they last placed the order. You know that for each and every customer now. Now that you have, and you can have more features. This is just an indicative solution I'm showing you, but you can absolutely have more features. If you want, you can have more features, like, okay, let's say you can break up the total order value into multiple categories and subcategories. You can say, hey, how many electronics orders were placed? How many grocery orders were placed? Right? How many uh, uh, stationary orders were placed? Something like that. And you can go to even more granular level of detail. You can say, hey, how many orders are placed on weekdays? How many orders on weekends? Total value of orders at night. Night is how you define night. Night is mostly um, 11 to 6, mostly. I think night is 11 to 6, 11 p.m. to 6 a.m. That's also a very interesting category. Who are the night owls? Who are the people who are usually shopping at night? Because I mean, see, these are all behavioral studies. You'll be surprised to know the kind of analytics that these kinds of companies are using, to make people buy more. And usually it is proven that maybe, because daytime we are all busy, no? Daytime we are all busy, we are all doing our work, we are very focused generally, right? So we know what to buy, we know what to do, but usually at night, our mind is idle, we are in our free time, and maybe your probability of purchasing is much more at night. Or let's just put it this way, your probability of getting influenced is much higher at night. So the companies will want to look at that also. So like for every customer, we want to see what is their total, purchase value, what is their nighttime purchase value, and if Amazon sees that, okay, your percentage of purchases at night is much higher, then you're a night owl. You're somebody who likes to purchase at night. They will look at your browsing time at night. So obviously in Amazon, they will not have your other, like they will see, okay, you're a customer who typically browses the application a lot at night compared to the mean and median averages. And once they do that, then they have a cluster. So if they do a customer segmentation, they will have a cluster. They have a cluster of people who are typically, buying more at night. And now for that group of people, they might want to send out more targeted campaigns for people who are, browsing at a particular point in time of the day. Okay, so maybe give you some offers, give you some discounts. So maybe, as I said, like they will influence you to purchase. So 50 rupees off they will give you, so you are forced to purchase. Anyway, so once we have this, this will be a bigger data set usually. So every customer will have multiple features. And once we have this data set, now we can carry on with the clustering. I've already shared the solution. You can go through this. So back to our elbow method. So we're getting two very distinct clusters, two very broad groups of data we are seeing. And this is a general concept. I talked about this in our poverty data set as well. So, the more groups you try to have, uh, the more difficult the problem will become, the more overlaps you will get. Two is a very clear cut segregation we are getting. So cluster one, cluster two, very clear cut segregation. Now, the moment you go beyond two, you might have a business case. You might have a business objective where you have to come up with more than two clusters. So that is you can't do anything about it. You have to do it. It could be a kind of a genuine business case for having more than two clusters. So you have to do it in that case, right? So that's the idea. Anyways, so this is the solutioning. And once you have the clusters, once you have the groups of data, you can now analyze the clusters. And you can clearly see these are the two broad groups of data we are able to see. So customers in group 0 typically have low frequency, low monetary value, and high recency. So that means customers in group 0 are not very high purchasers. So group 0 customers, you can clearly see, are not very high purchasers. They are customers with less orders, less monetary value, and high recency. They are typically not active. Whereas customers in group 1 are like my cash cows. These are customers who have high number of orders, high monetary value, they have a high value of orders, and also lower recency. They are more active. Maybe because they are more active, they are ordering more, they're purchasing more. So a lot of incredible insights you can start to get actually. But the labeling part is something you will have to do. This is a very basic data set, but if you're working with a more technical data set like your, as I said, networking data, your configuration data, then you will have to have the business insight. You have to understand, okay, what is this cluster? What kind of signals am I seeing there? And what is this cluster to? What kind of signals am I seeing there? So you will have to sit with a domain expert and understand. Or maybe let's say if I relate it back to the diabetes case study from yesterday, you identify there are two different groups of patients. So patients in group 1 exhibit a certain kind of behavior, and patients in group 2 exhibit a certain kind of behavior. So now you will have to sit with a domain expert and understand, hey, what is that behavior? What is group 1? What is group 2? How are they different? So these are some of the things that you will have to do. Okay, yeah. I have also shared another very interesting, this is just for your practice, and we can keep going on and on and on about case studies. I've actually shared a lot of case studies with you for reference. Obviously, as I said, one thing I've already clarified, this is a 1-year course, okay? This is a 1-year course that we are trying to really give you the best information in the shortest amount of time from an application perspective. So there's a lot of stuff that we have here, but the idea is to really focus on the things that are really important, the things that will help you solve real problems. That's what we are trying to focus on. So I've given a similar data set on iris. It's a very academic case study. You can go over it. Now that we know quite a bit of clustering, I think you can relate to this very well. You might be wondering, why have I shared the iris dataset as a clustering exercise? Because we already did one today with classification, right? So what I did here is I actually removed the labels, just like that. I just removed the label. So I actually took the data like this. So we had the class column. I removed the class column. So I took F1, F2, F3, F4, sepal length, sepal width, petal length, petal width, and we are just experimenting. Now, apparently, it turns out here that we have the labels. So we remove the labels, and we are solving it like a clustering problem. And let's see what we end up getting. The results will surprise you. So when we solve it like clustering, you will see the answers are surprisingly very similar, isn't it? See, the elbow method is clearly telling us that 1 to 2, 2 to 3, there are 3 distinct groups or clusters of data we are able to find. And now I take K means n clusters 3. So we do the clustering, and now we can actually compare the actual data, the actual labeled data, and the data that we are getting from clustering. So this is just one more school of thought I wanted to introduce. This might sound a little advanced right now, but you can see that this is another way you can actually compare or evaluate your clustering models. Because otherwise there is no way to evaluate your clustering models. We do not have any labeled data. Unlike supervised learning, where you have a training data, you build a model, you have a testing data, you have some ground truth y. So the model predicted some y and you're comparing with the actual y. There's a way to compare, right? Now in clustering, there is no way to compare. What do you do in clustering? How do you compare the predicted clusters with the actuals. This is exactly what I wanted to demonstrate through this very simple data set. Now, this is iris, but you can relate it to a far more complicated data set going forward. So the approach generally is that you take a semi-labeled data. The important term to mention here is semi-labeled data. You have some labels. So you sit with a domain expert who tells that, okay, these kinds of flowers are setosa, these kinds of flowers are virginica, these are versicolor. You sit with a domain expert to label some records. And then you hide the label column. You do it with a normal clustering based approach. You try to broadly figure out how many groups are there because you don't know that initially. Okay, you only have a few labels, right? And then you do clustering. And then you try to go and identify the different groups or clusters of data. And now you can compare. You can compare that, hey, I mean, this is the approach we are getting using clustering. And this is the original labels. And you know what? The best part is that you can go and now you can uh, evaluate the clustering model just like a classification model. Because if you see, this is the label 0, right? Take a look at this. This is the label 0, which is the blue color. It's in the middle, right? Similarly, the label orange is the versicolor. So the blue corresponds to versicolor. See how we can map it? So the blue here is the orange here. So 0 is versicolor. You can match the following. 0 is versicolor. Now this is the powerful thing. The moment you know 0 is versicolor, remember this was from the original label data, the semi-label data. Somebody would have given you few labels. This is like your ground truth right now. So now that you know that 0 is versicolor, now you have two things. You have model predicted 0. Actually, it is this. So you can actually create a confusion matrix and then you can create a classification report and you can evaluate a clustering model just like how we have done all through morning session today. Right? So this is just to introduce another school of thought. Because you have elbow method, you have silhouette coefficients, you have other kinds of coefficients are there to evaluate a clustering model in the absence of labels. But if you want to simulate some labels, if you want to think from a label perspective, you can have some semi-label data. You can have some amount of labels available. You can do your clustering the normal way. And then you can see that, hey, these are the predicted labels. These are the actual labels. And you can create a confusion matrix. You can say, hey, the clustering model predicted it is 0, which is setosa. You know what? Actually, it is versicolor. So some mistake happened. Then you can retrospectively try to improve and correct that mistake. Okay, so these are again some another very interesting thought that I wanted to share with all of you. How you can think of a clustering problem in a little bit of a different way. Okay, because something that I see you will be doing this in the real world a lot. Because in the real world you will have very limited number of label data. The amount of label data will be very limited, and this strategy can be used for generating more label data from a very limited amount of label data. You can use this clustering based approach to generate more labels actually. Okay, because you have lots of similar data points and you can generate more labels. So let's say you only got few labels for setosa, few labels for versicolor, few labels for virginica. And if you can do clustering properly, on that limited data, and if you know that, hey, all these flowers are very similar. If you label one as setosa, then they're all setosas, right? Okay, so now you say, hey, all these flowers in this group are very similar. So if you label one as versicolor, they're all versicolors. So by labeling a few data points, you have all of a sudden managed to label all the data points. And that's also a very powerful concept I wanted to discuss for clustering. See, I mean, this is the thing, like the algorithms are very simple, right? You can learn, you can memorize, you can implement it. It's very easy, but connect with the different ways you can do things, right? It's not just that, okay, clustering, you can use it only for finding groups of data. No, you can see this is another use case, right? So try to connect with these use cases. Okay,